Imagine looking up at the night sky and seeing something impossible. Not the familiar face of the moon, that pale disk that's been humanity's companion since before we were human, but instead a spreading cloud of glowing fragments, pieces of what was once whole, scattering across the darkness like luminous dust. The moon, that constant presence, that silent watcher of every night in human history, suddenly, impossibly, gone. Tonight, we're going to explore what would happen if the moon exploded. Not gradually crumbled, not slowly drifted away, but suddenly shattered, broke apart into countless pieces in a moment of cosmic violence. We'll imagine what Earth would become without its ancient companion, without the gravitational partner that's shaped our world for billions of years. Hello and welcome to the Sleepy Astronomer. If this is your first time drifting through the cosmos with me, welcome. I'm so glad you're here. And if you've travelled with me before through the quiet corners of space, it's wonderful to have you back for another journey into the impossible. Whether you're settling into bed, curled up in a favourite spot, or perhaps lying somewhere under that very moon we're about to imagine losing. I'm so grateful you're here to explore this question with me. If you enjoy these peaceful explorations of the cosmos, I'd be so grateful if you'd subscribe to join us for more cosmic journeys. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through space. Now, before we go any further, let me offer you this comfort. The moon is not going anywhere. Moons don't explode. They don't have internal heat sources or nuclear reactions. They're just rock and dust, held together by gravity, peacefully orbiting their planets. Our moon has been there for 4.5 billion years, and it will be there for billions more. What we're about to explore is pure imagination, a way of understanding what we have by imagining what it would be like to lose it. But here's what makes this question so fascinating. The moon does so much more than we usually realize. It's not just a light in the night sky, not just a romantic backdrop for poetry and songs. The moon stabilizes Earth's rotation. It creates our tides. It's shaped the evolution of life on our planet in ways both obvious and subtle. When you imagine losing it, when you walk through what would change, you begin to see all the invisible ways it shapes every day of your existence. Tonight we'll follow what would happen if the moon suddenly shattered. We'll watch debris fall from the sky in the most catastrophic meteor storm imaginable. We'll see Earth develop rings like Saturn's, beautiful and deadly. We'll explore how the tides would stop, how nights would become darker, how Earth's very rotation would change. We'll discover what this means for life, for ecosystems, for the long-term stability of our planet. And perhaps most importantly, we'll learn what this impossible scenario teaches us about the remarkable companion we actually have. The moon that's been there every night, stabilizing our world, creating the tides, lighting the darkness. The moon that connects us to every human who's ever lived, because they all saw the same moon we see tonight. So settle in, take a deep breath, let yourself relax into this journey. The question is simple: what would happen if the moon exploded? The answer? Well, the answer will take us through meteor storms and ring systems, through changing tides and wobbling planets, through darkness and adaptation and the deep time of geological change. Before we imagine losing the moon, we should probably spend some time appreciating what it actually does for us. Because the moon isn't just a pretty light in the sky, it's not just there for decoration, or to inspire poets, or to give werewolves something to howl at in movies. The moon is actively shaping our world every single day, in ways that are both obvious and surprisingly subtle. Let's start with the most visible gift the moon gives us: the tides. Twice a day, in most places on Earth, the ocean rises and falls. Water creeps up the beach, then retreats. Harbours fill and empty. Tide pools appear and disappear. This has been happening for as long as there's been an ocean, for billions of years, with such regularity that we barely think about it. But it's not automatic. It's not just something oceans do. It's caused by the moon. Here's how it works. The moon has gravity, not as much as Earth since it's smaller, but enough to pull on things. And it pulls on our oceans. The water on the side of Earth facing the moon gets pulled toward the moon, creating a bulge. You might think that would create one high tide, but here's the interesting part. There's also a bulge on the opposite side of Earth. This happens because Earth itself is being pulled toward the moon, but the water on the far side is pulled less, so it bulges outward relative to the planet. As Earth rotates, different parts of the planet move through these bulges. When you're in a bulge, you experience high tide. When you're between bulges, you experience low tide. And because there are two bulges, you get 2 high tides and 2 low tides each day. It's an elegant system, this gravitational dance between Earth and Moon. Now the Sun also creates tides. It has gravity too, after all. But the Sun's tidal effect is only about 1/3 as strong as the Moon's. When the Sun and Moon align during new and full moons, their tidal effects add together, and you get especially high and low tides called spring tides. When they're at right angles during the quarter moons, their effects partially cancel out, and you get weaker tides called neap tides. This might all seem like interesting physics, but not particularly important to daily life. After all, if you don't live near the ocean, tides might seem irrelevant, but tides do more than just make water go up and down. They're essential to coastal ecosystems. The intertidal zone, that strip of coast between high and low tide, is one of the most productive ecosystems on Earth. Organisms there have evolved to handle the constant change between being underwater and being exposed to air, barnacles close up tight when the tide goes out. Mussels filter food from the water when it's in, then wait patiently when it's out. Crabs scuttle around tide pools. Shorebirds time their feeding to the tides, knowing exactly when the mudflats will be exposed and full of tiny creatures to eat. Without tides, this entire ecosystem would collapse. The intertidal zone would become either permanently dry land or permanently underwater, and all the species specifically adapted to that twice-daily transition would have nowhere to live. Tides also help mix the ocean. They drive currents, especially in coastal areas and straits. They stir up nutrients from the bottom, making them available to organisms near the surface. They help maintain the ocean's circulation patterns. The ocean is not a static pool of water. It's constantly moving, mixing, circulating, and tides are part of what keeps it that way. But the moon does something else for Earth. Something even more important than tides, though it's less obvious. The moon stabilizes our planet's rotation. Earth spins on its axis, which is tilted at about 23.5 degrees relative to the plane of our orbit around the Sun. This tilt is why we have seasons. When your hemisphere is tilted toward the Sun, you get summer. When it's tilted away, you get winter. The tilt stays relatively constant, year after year, century after century. But without the moon, it wouldn't. Earth's tilt would wobble. Over millions of years, it could swing wildly, from nearly 0 degrees to as much as 85 degrees. And those changes in tilt would cause dramatic climate shifts. We know this happens because we can see it happening to Mars. Mars has 2 tiny moons, Phobos and Deimos, but they're far too small to stabilize its rotation the way our moon stabilizes ours. As a result, Mars's axial tilt varies dramatically over millions of years. Sometimes it's tilted at 15 degrees, sometimes at 35 degrees or more. This causes its climate to swing from relatively stable to chaotic. Earth would face the same problem without the Moon. The tilt would be influenced by the gravitational pull of other planets, by the distribution of mass in Earth's crust, by various orbital factors, and over geological time it would drift, wobble, swing to extremes. Seasons would become unpredictable. Ice ages would come and go on schedules that life couldn't adapt to. The stable climate that allowed complex life to evolve would be lost. The Moon prevents this. Its gravity acts like a gyroscope, keeping Earth's tilt stable within a narrow range. The tilt does vary slightly. It oscillates between about 22.1 and 24.5 degrees over a 41,000-year cycle. But these are small changes, manageable changes, the kind of variation that life can adapt to. The Moon also affects Earth's rotation in another way. It's slowing us down. Very gradually, through tidal friction, the Moon is making Earth's days longer. About 620 million years ago, a day was only 22 hours long. The Moon's gravitational pull on our tidal bulges acts as a brake, very slowly transferring angular momentum from Earth's rotation to the Moon's orbit. This process continues today. Days are getting longer by about 1.7 milliseconds per century. That's not much, you won't notice it in your lifetime, but over geological time it adds up. In the far future, billions of years from now, Earth and the Moon might become tidally locked to each other, the way the Moon is already tidally locked to Earth. One side of Earth would always face the Moon, and a day would last about a month. Of course, the Sun will have other plans for us long before then, but that's a different story. Let's talk about moonlight for a moment. The Moon provides light at night. Not much, about 1/400,000th the brightness of the Sun, but enough to see by enough to cast shadows on a clear night. Enough that before artificial lighting, it made a significant difference to human activities. A full moon provided enough light to travel by, to work by, to hunt by. Many cultures plan their activities around the lunar cycle. Harvest moons, hunters' moons. These weren't just poetic names, they were practical indicators of when you'd have enough light to do important work after sunset. And it's not just humans who use moonlight. Many nocturnal animals rely on it. Owls hunt by moonlight. Moths navigate using the moon as a reference point, which is why they spiral around artificial lights. They're trying to maintain a constant angle to what they think is the moon, but a nearby light source completely confuses their navigation system. Some species time their reproduction to the moon. Corals spawn in synchronized events tied to the lunar cycle. Sea turtles nest during certain moon phases. Various fish species spawn according to the moon. There's even evidence that some trees and other plants respond to moonlight, though the mechanisms aren't fully understood. The moon has shaped life on Earth not just through its physical effects, tides and stability, but through the simple fact of its presence, its light, its reliable cycle from new moon to full moon and back again. And there's something else, something harder to quantify, but no less real. The moon has been humanity's companion throughout our entire existence as a species. Every human who has ever lived has seen the moon. It's connected us across time and culture. The same moon that our ancestors saw thousands of years ago is the same moon we see tonight. Ancient Egyptians saw it. Medieval Europeans saw it. Indigenous peoples across every continent saw it. And we still see it. The continuity is rare in the universe. We're here for such a brief time, individuals and civilizations both. But the moon endures. It was there before us, and will be there after us. It's a kind of cosmic constant, a touchstone that connects us to the deep time of our planet's history. The moon formed about 4.5 billion years ago, most likely from debris created when a Mars-sized object crashed into the early Earth. This collision was catastrophic. It likely melted the surface of our planet and sent enormous amounts of material into orbit. That orbiting debris eventually coalesced into the Moon. So in a strange way, the Moon is made of Earth. It's our planetary sibling born from the same violent event, and it's been orbiting us ever since, slowly spiralling outward at about 3.8 centimeters per year. It was once much closer. Early in Earth's history, the Moon would have appeared much larger in the sky, and the tides would have been far more extreme. But it's been drifting away very slowly for billions of years. Eventually, in the very distant future, it will be far enough away that total solar eclipses will no longer be possible. The Moon will appear too small to completely cover the Sun, but that won't happen for hundreds of millions of years. For now, we're in a special time when the Moon appears to be almost exactly the same size as the Sun in our sky, making total eclipses possible. This relationship between Earth and Moon is sometimes called a binary planet system, rather than a planet with a satellite. Our Moon is unusually large relative to Earth, about 1/4 Earth's diameter. Most moons in the solar system are tiny compared to their planets, but our Moon is substantial. It's a partner, not just a satellite. And this partnership has shaped both bodies. The Moon is tidally locked to Earth, always showing us the same face. Earth's rotation is slowed and stabilized by the Moon. We've evolved together in a gravitational embrace that's lasted for billions of years. So when we imagine losing the Moon, we're not just imagining losing a light in the sky. We're imagining losing the tides, losing the stability of our seasons, losing the light that countless species depend on, losing a companion that's been with us since before there was life on Earth. That's what makes this scenario worth exploring. Not for the disaster of it, but for the appreciation. By imagining what we'd lose, we can better understand what we have. By walking through the consequences of the Moon's absence, we can see all the ways, obvious and subtle, that it shapes our world. The Moon is a gift, and we're about to imagine what happens when that gift is suddenly, violently taken away. So we've established what the Moon does for us, what it means to our planet, how it shapes our world in both obvious and subtle ways. Now let's imagine the impossible. Let's imagine that somehow, against all the laws of physics that make this scenario extremely unlikely, the Moon shatters. First, we need to acknowledge something important. Moons don't just explode on their own. The Moon is geologically dead. It has no molten core, no volcanic activity, no internal heat to speak of. It's just rock and dust, held together by its own gravity, quietly orbiting Earth as it has for billions of years. There's nothing inside it that could cause an explosion. But we're imagining anyway. Maybe a massive asteroid hits it at exactly the wrong angle. Maybe there's some impossible physics we don't understand. Maybe, and this is purely for the sake of our exploration, aliens decide to test some weapon they really shouldn't be testing. The how doesn't matter as much as the what happens next. So let's say it's a clear night. The Moon is full, bright, hanging in the sky the way it's done countless times before. And then, suddenly, it isn't. What you'd see would depend on where you are and how you're looking at it. If you happen to be watching the Moon through a telescope, you'd see it first. A flash perhaps, a sudden brightening. And then the shape begins to change. The familiar round disk starts to distort, to fragment. Pieces separate. The Moon stops being one object and becomes many objects. From Earth, with the naked eye, the change would be more gradual. At first, the Moon might still look relatively whole. Even after shattering, gravity would hold the pieces close together for a brief time. but over minutes and hours you'd notice the shape becoming irregular. The bright disk would start to look fuzzy around the edges as fragments drift apart. And then the sky would start to fill with light. Because here's what happens when you break the moon into thousands or millions of pieces. You suddenly have thousands or millions of surfaces reflecting sunlight. Instead of one bright disk, you have a spreading cloud of glowing fragments. Some pieces catch the light at different angles. The moon transforms from a solid object into something that looks almost like glitter scattered across the night sky. It would be beautiful, in a terrible sort of way. The kind of beauty that makes you forget, just for a moment, that you're watching a catastrophe unfold. The sky would shimmer with reflected light, brighter than any full moon, because you'd have so much more surface area reflecting the sun. It might almost be bright enough to read by, certainly bright enough to cast shadows. People around the world would notice immediately. Even people who normally don't pay attention to the sky would see that something was wrong. The moon doesn't look like that. The moon doesn't spread out, doesn't become a cloud of light. Social media would explode with photos and speculation astronomers would scramble to figure out what was happening. Governments would probably panic, though what they'd do about it is unclear. Because there's nothing you can do about it. Once the moon is shattered, the physics takes over. The fragments would begin to interact gravitationally. Each piece pulls on every other piece. Larger fragments would have more gravity, would start to collect smaller pieces. Some fragments would collide and merge. Others would collide and shatter further. The cloud of debris would be chaotic. Thousands of pieces all moving in slightly different orbits, all influencing each other. Some pieces would have enough velocity to escape Earth's gravity entirely. They'd be flung out into space, becoming asteroids in orbit around the Sun. Earth would briefly become a planet that sheds debris, scattering pieces of its former moon across the inner solar system. Future space missions might encounter chunks of moon rock in unexpected places. Other pieces would be moving too slowly to maintain orbit. They'd begin to fall. Not all at once. The different pieces are at different distances, moving at different speeds. But over the following hours and days and weeks, more and more fragments would begin their final journey toward Earth. And here's where we need to talk about the Roche limit, because it's relevant to what happens next. The Roche limit is the minimum distance at which an object held together only by its own gravity can orbit another object without being torn apart by tidal forces. For Earth and a moon-like object, the Roche limit is about 9,500 kilometers from Earth's center, or roughly 3,100 kilometers above Earth's surface. The moon orbits at about 384,000 kilometers from Earth, well outside the Roche limit. This is why it hasn't been torn apart naturally. But once we've shattered it, once it's no longer one cohesive object, the pieces behave differently. Small pieces don't have enough self-gravity to be affected by tidal forces. They can orbit wherever they want. Larger pieces might be pulled apart further if they drift too close to Earth. So the debris cloud would sort itself. The smallest pieces, pebbles, dust, would stay in various orbits or fall to Earth. Medium-sized pieces, boulders, small mountains might break up further as they approach the largest pieces. Chunks the size of cities or small asteroids would either stay in orbit or begin a controlled descent, depending on their trajectory. And this debris cloud, this expanding collection of moon fragments, would gradually form a ring system around Earth. Not immediately. At first, it would just be a chaotic cloud. But over time, days, weeks, months, the debris would spread out along the moon's former orbit. Pieces would collide, fragment further, distribute themselves into a more uniform band. What was once a sphere would become a ring, like Saturn's rings, but made of moon rock instead of ice. This ring would be visible from Earth as a bright band across the sky. If you were standing at the equator, you'd see it arch directly overhead, stretching from horizon to horizon. At higher latitudes, it would appear as an arc across the sky. From the poles, you wouldn't be able to see it at all. The ring would be edge-on, too thin to see from that angle. The ring would be brightest when the sun was behind you, reflecting off countless fragments. It would dim when the sun was in front of you, with the fragments appearing dark against the day sky. At night, the ring would glow, illuminated by the sun, even when Earth's surface was dark. It would fundamentally change what our sky looks like. No more lone moon rising in the east and setting in the west. Instead, a permanent fixture, a band of light that never moves relative to the stars, because it's orbiting Earth just as Earth rotates beneath it. Children born after the explosion would grow up thinking rings in the sky are normal. The moon, that round disk in old photos and videos, would seem as strange to them as the absence of rings seems to us. But the rings wouldn't be stable, not on geological timescales. Particles in the ring would collide with each other, would slowly lose energy, would gradually spiral inward toward Earth. Some would burn up in the atmosphere as meteors. Some larger pieces would survive to hit the surface. The ring system would be slowly raining down on Earth, a process that would continue for thousands or millions of years. This is actually how planetary rings work. They're not permanent features. Saturn's rings, spectacular as they are thought to be relatively young, maybe only a few 100 million years old. They're slowly disappearing, slowly spiraling into Saturn. In the far future, Saturn might not have rings at all. Earth's new rings would face the same fate. They'd be temporary on cosmic timescales, but temporary can still mean a very long time by human standards. Now, let's talk about what happens to the pieces that don't form the ring, the pieces that are falling. The Moon has a mass of about 7.3 times 10 to the 22nd kilograms. That's a lot of rock, and while some of it escapes into space and some forms a ring, a significant portion would be on trajectories that intersect with Earth. These pieces would arrive over an extended period, not all at once, thankfully, but in waves. The smallest pieces would burn up harmlessly in the atmosphere, creating meteor showers more spectacular than any we've ever seen. You'd see dozens, then hundreds, then thousands of meteors per hour. The night sky would be full of streaks of light as moon dust enters the atmosphere at high velocity and vaporizes. Medium-sized pieces, objects the size of cars or houses, would make it through the atmosphere partially intact. They'd fragment during entry, but chunks would reach the surface traveling at tremendous speed. Each impact would release energy equivalent to a large bomb. One piece hitting a city could level it completely. And the largest pieces, chunks of moon kilometers across, would be absolutely catastrophic. These would hit with energies comparable to nuclear weapons, or worse, they'd create massive craters, would throw dust into the atmosphere, would trigger earthquakes and possibly volcanic eruptions. If one hit an ocean, the tsunami would devastate coastlines thousands of miles away. The good news, if there is good news, is that these large pieces would be relatively rare. Most of the moon would fragment into smaller pieces, but even a few large impacts would be civilization-threatening events. The bombardment would be heaviest in the first few weeks after the explosion. That's when most of the fragments on immediate collision courses would arrive. After that initial wave, impacts would become less frequent, but would continue sporadically for years, decades, possibly centuries. Every time two pieces in the ring collided and knocked each other into lower orbits, you'd get another wave of meteors. Living on Earth during this period would mean living with constant danger from above. You'd never know when or where the next impact would occur. Weather forecasting would be the least of your concerns. You'd need meteor forecasting, trying to track thousands of pieces of debris and predict their trajectories. Some regions would be hit harder than others just by chance. Some would escape with minimal damage, but nowhere on Earth would be truly safe. The debris would be distributed across all latitudes, all longitudes. It would be a global catastrophe. And through all of this, through the beautiful horror of the fragmenting moon and the deadly rain of debris, people would be trying to make sense of what happened. Scientists would be studying the pieces that land, trying to understand what caused the explosion. Governments would be coordinating rescue efforts, trying to protect populations, trying to maintain some semblance of order as the world above literally falls apart. There would be wonder mixed with a fear, because even as pieces of moon rain down, even as the world deals with impact after impact, the sky would be putting on a show unlike anything in human history. The spreading debris cloud, the forming rings, the spectacular meteor showers. It would be beautiful. Terrifying, yes. Deadly, absolutely. But also beautiful. That's the thing about cosmic events. They don't care about our feelings, our fears, our survival. They just are. They follow physics, not morality. And sometimes physics creates spectacles that are both destructive and gorgeous. The moon broken into pieces, falling from the sky, forming rings around our planet. It would be one of those spectacles, the kind of thing that would be remembered for as long as there were humans to remember it. The night the moon shattered, the year the sky changed forever. But we're getting ahead of ourselves. We've watched the moon break apart and seen the debris begin to fall and form rings. Now we need to follow what happens next. We need to explore the full consequences of losing our companion, of Earth suddenly becoming a planet without a moon, a planet with rings, a planet under bombardment. That's a story that will unfold over days, years, millions of years. Because this isn't just an immediate catastrophe. It's a change in Earth's fundamental nature, a transformation that will echo through geological time. The explosion is just the beginning. We've watched the moon shatter and seen the debris begin to spread. Now we need to follow what happens as that debris comes down, because gravity doesn't forget, and what goes up, or in this case, what gets blown apart in orbit, eventually comes down. The meteor storm wouldn't start immediately. Remember, the moon is about 384,000 kilometers away. Even fragments moving at several kilometers per second would take hours or days to reach Earth, depending on their exact trajectories. So there would be this strange grace period after the explosion, where the moon is visibly broken, but the consequences haven't reached us yet. During those hours, people would be watching the sky, tracking the spreading debris, trying to calculate which pieces were headed our way. Astronomers would be working frantically, telescopes pointed upward, computers running trajectory calculations. Governments would be trying to figure out where to evacuate people, though the honest answer would be, we don't really know where it's going to hit. Because this isn't like tracking a single asteroid. This is tracking thousands or millions of pieces, all moving independently, all influencing each other gravitationally, all potentially changing course as they collide with other pieces. It would be the most complicated orbital mechanics problem anyone had ever attempted to solve. And then the first pieces would start arriving. The smallest fragments would come first, dust particles, grains of sand, tiny chips of rock. These would hit the upper atmosphere and burn up completely, vaporizing from friction before they got anywhere near the surface, and there would be a lot of them, so many that the sky would start to glow. Normally, when you see a meteor, a shooting star, it's a brief flash, a piece of dust burning up in a fraction of a second. But when you have millions of particles entering the atmosphere constantly, the sky doesn't flash, it glows. A steady, eerie luminescence, brightest in the direction of the debris cloud, but visible across the entire sky. This glow would start faint but build over hours. The atmosphere would be doing exactly what it's supposed to do, protecting us from space debris, but it would be working overtime. All that friction, all those particles burning up, would be heating the upper atmosphere. Not dangerously, not at first, but enough to notice the sky would feel more active, more alive than it ever has. And then the larger pieces would start to arrive. Objects the size of pebbles would make it deeper into the atmosphere before burning up. They'd create bright meteors, streaks of light that would last for seconds rather than fractions of seconds, and there wouldn't be 1 or 2 per hour, like during a normal meteor shower. There would be dozens per minute, then hundreds. The sky would be full of streaking lights, like some cosmic fireworks display that never ends. For a brief moment, if you didn't know what was happening, if you didn't understand the danger, it would be one of the most beautiful things you'd ever seen. The night sky absolutely alive with light, more meteors than you could count, each one a brilliant streak painting temporary lines across the darkness. But of course, you would know what was happening, and you'd know what comes next. Objects the size of basketballs or small boulders would make it through the atmosphere partially intact. They'd fragment during entry, the heat and stress would break them apart, but pieces would reach the surface and they'd be moving fast, very fast. When something hits Earth's atmosphere at orbital velocity, around 11 kilometers per second or more, it's carrying tremendous kinetic energy. A rock the size of a basketball, weighing maybe 10 kilograms, hitting the ground at even a fraction of orbital velocity, would impact with the energy of a large bomb. Not enough to destroy a city, but certainly enough to destroy a building, or several buildings, if it fragmented into multiple pieces that spread out. And these wouldn't be rare, isolated impacts. They'd be happening constantly. One here, one there, dozens per hour, then hundreds. The sound of impacts, distant thunder-like booms, would become a constant background noise. Sirens would be wailing continuously. Emergency services would be overwhelmed immediately. There would be no way to respond to every impact, no way to rescue everyone who needed help. The randomness of it would be particularly terrifying. You could be in a shelter, underground, thinking you're safe, and then hear an impact nearby. Or you could be exposed, watching the sky, and see meteors all around you, but have none land close. It would be pure chance. Cosmic roulette. Then the really big pieces would start arriving. Objects the size of cars or houses, or in the worst cases, small mountains. These are the ones that would cause catastrophic damage. Let's think about what happens when a large piece of moon rock hits Earth. Say, a chunk about 10 meters across weighing maybe 1,000 tons. It enters the atmosphere, and unlike the smaller pieces, it doesn't burn up completely. The outer layer ablates away, melts and vaporizes, but the core remains solid. The friction with the atmosphere barely slows it down, and then it hits. The impact would release energy equivalent to a small nuclear weapon. The rock would vaporize on contact, along with whatever it hit. The shock wave would flatten everything for miles around. If it hit land, you'd get an instant crater hundreds of meters across. If it hit an ocean, you'd get a tsunami that would devastate coastlines. And here's the terrifying part. Based on the mass of the moon and the percentage that would be on Earth-crossing trajectories, you'd expect dozens or possibly hundreds of these large impacts. Not all at once, thankfully. They'd be spread out over weeks or months. But that's still dozens of civilization-ending events happening in rapid succession. One impact might destroy a major city. Another might trigger earthquakes across an entire region. A third might hit the ocean and send tsunamis racing across multiple oceans. There would be no safe place, no region that could be sure it wouldn't be hit. The impacts would also throw enormous amounts of dust into the atmosphere. Each large impact would blast rock and soil into the stratosphere, where it would spread around the globe. And with many impacts happening, the cumulative effect would be significant. The dust would block sunlight, similar to what happened when the asteroid killed the dinosaurs. Temperatures would drop. Not immediately, there's a lot of thermal inertia in Earth's climate system, but over weeks and months, the average temperature would fall, agriculture would be disrupted, growing seasons would be affected. This is impact winter, and it would come on top of all the direct destruction from the impacts themselves. The duration of the bombardment would depend on the orbital dynamics of the debris. The initial wave, the pieces that were on immediate collision courses when the moon exploded, would hit over the first few days or weeks. These would be the most intense period, when impacts would be most frequent. After that initial wave, things would calm down somewhat, but not entirely. The debris cloud would continue to evolve. Pieces in the forming ring would collide with each other, and those collisions would knock some fragments into lower orbits. Every so often, another wave of debris would come down. This would continue for years, maybe decades, possibly centuries. As long as the ring system existed, as long as there was debris in orbit colliding and fragmenting, and occasionally falling, Earth would be subject to sporadic bombardment. You'd learn to live with it in a way. The constant low-level danger would become normalized. Meteor warning systems would become as common as weather alerts. Buildings would be designed with reinforced roofs. Cities would develop crater repair protocols. It would be like living in a war zone, except the enemy is physics and there's no one to negotiate a ceasefire with. Let's talk about the psychological impact of all this, because it would be significant. Humans generally like to feel safe, to feel that their environment is predictable and controllable. We build houses with roofs because we don't like rain. We build walls because we want privacy and security. We create systems and structures that give us the illusion that we're in control of our surroundings. The meteor bombardment would shatter that illusion completely. You could do everything right, be in a shelter underground away from windows, and still be killed by a rock that happened to hit directly above you. Or you could ignore all safety protocols and be fine because no rocks happened to hit near you. Survival would come down to luck more than anything else. This randomness, this lack of control, would be psychologically devastating for many people. Some would adapt, would learn to accept the new reality. Others would struggle, would be paralyzed by fear, or would engage in increasingly irrational behavior, trying to feel safe. There would also be the grief of loss. Not just personal losses, friends, family members killed by impacts, but collective loss. The loss of cities and landmarks and familiar places, the loss of infrastructure and technology, the loss of the world as it was. Every impact would be erasing a piece of human civilization, and the cumulative effect would be staggering. And there would be no one to blame. When a war destroys cities, you can at least blame the enemy. When a disease kills millions, you can blame the pathogen, or lack of preparation, or bad luck. But this would be pure cosmic bad luck. The moon exploded for reasons beyond our understanding or control, and now the consequences are raining down on us. There's no enemy to fight, no disease to cure, no policy to implement that would make it stop. You just have to wait it out and hope. Waiting while pieces of your former moon fall from the sky is a special kind of hell, existentially speaking. But let's talk about what would survive, because not everything would be destroyed. Even in the worst-case scenarios, with hundreds of major impacts, most of Earth's surface would remain untouched. The impacts would be devastating to the areas they hit directly, but Earth is large. There would be regions that escaped major impacts entirely, just by chance. Underground structures would fare better than surface structures. Deep mines, subway systems, bunkers, these would offer real protection from all but the largest impacts. People in these shelters would be safe from the meteor storm, at least physically. They'd still have to deal with the psychological stress, the disruption of supply chains, the collapse of global systems, but they'd be alive. Coastal areas would face additional danger from tsunamis triggered by ocean impacts, but inland regions far from coasts would be spared. That particular threat, mountains, would offer some protection. Meteors hitting mountains would waste their energy, excavating rock instead of devastating population centers. Deserts, already sparsely populated, would absorb many impacts without causing human casualties. The distribution of impacts would be roughly random, but with some patterns. The debris would be orbiting Earth, and objects tend to hit the side of a planet that's moving forward in its orbit. There might be slightly more impacts on one hemisphere than the other. Equatorial regions would see more impacts than polar regions because of orbital inclinations. But these are statistical patterns. Any individual location could be hit or spared. Marine life would be affected, but might fare better than land life. The ocean is deep and provides excellent protection from anything but direct hits. A meteor hitting the ocean surface would create a huge splash and possibly a tsunami, but the actual impact energy would be absorbed by the water. Fish kilometers below the surface wouldn't even notice most impacts. Deep-sea ecosystems, especially those around hydrothermal vents that don't depend on sunlight anyway, would be largely unaffected. They're already living in permanent darkness under crushing pressure in an environment that's hostile to most life. A few more rocks falling from the sky. That's nothing compared to their daily existence. So life would survive, certainly. The question would be what kind of life and how much of it. A bombardment of this scale would likely cause a mass extinction event. Not the worst in Earth's history. That honour goes to the Permian extinction that killed over 90% of species, but significant. Comparable, perhaps, to the extinction that killed the dinosaurs. Large land animals would be particularly vulnerable. They can't hide underground easily. They need a lot of food, and they're affected by the impact winter that would follow the bombardment. Small animals that can burrow, that have low metabolic needs, that can survive on whatever scraps of food remain. They'd have better odds. Plants would struggle with the reduced sunlight from the dust, but many have seeds that can survive for years waiting for better conditions. Forests might be devastated, but new forests would eventually grow. The fundamental ecology of Earth would be disrupted, but not destroyed. And humans? Well, humans are remarkably adaptable. We're generalists. We can eat a wide variety of foods. We can live in a wide range of environments. We're smart enough to build shelters and plan ahead and work together. Even in a scenario this catastrophic, some humans would survive. But civilization as we know it would not. The global supply chains, the technology, the cities, the infrastructure, most of that would be gone. We'd be starting over, rebuilding from whatever remained, learning to live in a world where pieces of moon occasionally fall from the sky without warning. It would be a different world, a harder world, a world where the night sky glowed from constant meteor activity, where tsunamis from ocean impacts were a regular occurrence, where you learn not to get too attached to buildings because they might not be there tomorrow, but it would still be Earth, still our home, still the only planet we have. And we'd make do, because that's what humans do. We adapt, we survive, we rebuild. The meteor storm, terrible as it would be, would eventually end. Not quickly. It might take decades or centuries before the last significant pieces fell, but it would end. The debris would either hit Earth, get captured into stable orbits, or be ejected from the system entirely. And when it finally did end, when the last major impact occurred and the bombardment faded to occasional small meteors, Earth would still be here. Changed, yes. Scarred, certainly, but here. Spinning under its new rings, with a thinner atmosphere and a wounded biosphere, but still capable of supporting life. The moon would be gone, broken into pieces, some fallen to Earth, some orbiting as rings, some scattered across the solar system, but Earth would remain, and life, stubborn and resilient as always, would continue. We've watched the moon shatter and followed the meteor bombardment. Now let's talk about what stays up there, what doesn't fall, what remains in orbit, creating something Earth has never had before. Rings. When we think of planetary rings, we naturally think of Saturn. Saturn's rings are one of the most iconic sights in the solar system. Those beautiful, delicate bands stretching hundreds of thousands of kilometers across space. They're made mostly of ice particles, ranging in size from grains of sand to house-sized chunks, all reflecting sunlight in a spectacular display. Earth's rings would be different. They'd be made of moon rock, not ice. They'd be darker, less reflective, but they'd still be spectacular in their own way, because when you break up an entire moon and spread its debris into a ring system, you create something that fundamentally changes what your sky looks like. The rings would form gradually. After the initial explosion and the bombardment period, the debris that remained in orbit, the pieces that didn't fall to Earth and didn't escape into space, would begin to organize itself. Collisions between particles would cause some to speed up and others to slow down. Over time, the debris would spread out along the former orbital path of the Moon, creating a band of material encircling Earth. From the surface, if you were standing at the equator, you'd see the rings arch directly overhead, a bright band stretching from one horizon to the other, crossing the sky at the zenith. During the day, if the angle was right, you might see the rings as a faint line against the blue sky. At night, they'd be brilliant, reflecting sunlight even when the ground below was in darkness. The appearance would change depending on your latitude. At the equator, the rings would be a band overhead. As you move toward the poles, the rings would appear lower in the sky, arching across the horizon rather than overhead. At around 45 degrees latitude, roughly where cities like Portland, Lyon or Hokkaido are located, the rings would be a graceful arc, rising from the horizon on one side and setting on the horizon on the other. And from the poles themselves, you wouldn't be able to see the rings at all. You'd be looking at them edge-on, and even a ring system thousands of kilometers thick would appear as just a thin line, too narrow to see from that angle. It's one of those quirks of geometry. The most spectacular feature in Earth's new sky would be completely invisible from certain latitudes. The rings would be brightest during certain times of the year. When Earth's tilt meant the rings were angled to catch more sunlight, they'd shine brilliantly. When the angle was less favorable, they'd appear dimmer. This would create a new kind of seasonal variation in the night sky, one that had nothing to do with the stars or planets, but entirely with how Earth was oriented relative to the Sun and its own rings. During certain alignments, the rings would cast shadows on Earth. This would happen when the Sun, the rings, and a portion of Earth's surface lined up. you'd see a shadow band moving across the landscape like a very strange, very geometric eclipse. These shadow events would be predictable, would occur at regular intervals based on Earth's orbit and rotation. Ancient peoples would probably have built calendars around them, the way they built calendars around lunar phases. The rings would also cause a unique phenomenon: ring shine. Just as we currently have moonlight, light from the sun reflected off the moon, we'd have ring light. On certain nights, even when there was no moon, the sky would be illuminated by light reflecting off the rings. It wouldn't be as bright as a full moon used to be, but it would be noticeable enough to navigate by, enough to cast faint shadows, enough to change what we consider a dark night. This ring shine would be particularly noticeable at the equator, where the rings would be directly overhead and would illuminate the ground evenly. At higher latitudes, the rings would be at an angle, creating more directional lighting. The quality of nighttime would fundamentally change. True darkness would be rarer, limited to specific times and places when the geometry blocked the ring shine. Now let's talk about how rings actually work, because they're more dynamic than they might appear. Each particle in the ring is in its own orbit around Earth. They're not connected, not touching. They're all independent objects, from dust grains to boulders, each following its own trajectory based on its velocity and distance from Earth. But they do interact. Particles collide with each other constantly. These collisions can be gentle, two dust grains bumping and slightly changing each other's trajectory, or they can be violent, two boulder-sized chunks smashing together and fragmenting into dozens of smaller pieces. The ring is constantly evolving, constantly rearranging itself through these endless collisions. Gravity also plays a role. Larger chunks in the ring have their own gravity, small as it is, and can attract smaller particles. Over time, this can lead to some clumping, some areas of the ring becoming denser, while others become more sparse. The ring wouldn't be uniform. It would have structure, bands of higher and lower density, possibly gaps where resonances with Earth's rotation have cleared out material. These gaps would be similar to the gaps in Saturn's rings, which are caused by gravitational resonances with Saturn's moons. Earth doesn't have multiple moons anymore, obviously, but the Sun's gravity and Earth's own rotation create similar resonance effects. The rings would develop patterns, structures, a complexity that would make them endlessly fascinating to study. And they wouldn't be stable, not over the long term. Particles in the ring would gradually lose energy through collisions. As they lost energy, they'd spiral inward, getting closer to Earth. Eventually, they'd hit the upper atmosphere and burn up as meteors. The ring would be slowly raining down on Earth, a process that would continue for thousands or millions of years. This means that the meteor bombardment we discussed in the last chapter wouldn't truly end. It would taper off after the initial waves, yes, but it wouldn't stop completely. As long as the rings existed, there would be a steady drizzle of meteors entering the atmosphere. Most would be small, harmless, creating a near-constant meteor shower that would become the new normal, but occasionally larger pieces would come down and you'd get a more significant impact. Living under rings would mean living with this constant meteor activity. You'd get used to seeing meteors, to hearing them sizzle through the atmosphere. Certain times of year, when the ring was particularly active, or when Earth's rotation brought you through a denser part of the ring, meteor activity would increase. Other times it would decrease. It would become part of the rhythm of life, like seasonal rains or temperature changes. The rings would also be a hazard for anything trying to leave Earth. Satellites, space stations, crewed missions to space. All of these would have to navigate through the ring to get beyond Earth orbit, and the ring would be full of debris moving at orbital velocities. A collision with even a small particle at those speeds would be catastrophic for a spacecraft. This means that space travel, already difficult, would become significantly more dangerous. We'd lose our satellite infrastructure, weather satellites, GPS, communication satellites. They'd be destroyed by ring debris within weeks or months of the moon's explosion, and replacing them would be nearly impossible. Any new satellite would have to either operate below the ring system, in a very low orbit with its own challenges, or somehow get through the ring unscathed, which would be a gamble at best. The International Space Station, if it somehow survived the initial explosion and bombardment, would not survive the ring. The ring would grind it down, one collision at a time, until nothing remained but more debris to add to the ring. So we'd be cut off in a sense, stuck on the surface of our planet, unable to safely venture into space, at least not until the ring dissipated enough to make passage possible. This could take thousands of years. We'd have a long wait before we could be a spacefaring civilization again. But let's talk about the beauty of the rings, because despite all the destruction and danger, they would be undeniably beautiful. Imagine looking up on a clear night and seeing a luminous band stretching across the entire sky. Imagine watching how it changes with the seasons, how it catches the light differently at different times of year. Imagine the patterns and structures visible with even a small telescope, the gaps, the density waves, the variations in brightness. Children growing up under these rings would think they were normal. They'd draw pictures of Earth with rings, the way we draw Saturn with rings. They'd learn about how the rings formed, about the moon that used to be there, about the catastrophe that changed the sky forever. But to them, the rings would be part of what Earth is. The idea of a blank sky, with just a moon and stars, would seem strange, almost empty. There would be new forms of art inspired by the rings. Painters would depict landscapes with the ring arch in the background. Poets would write about ring shine and shadow bands. Musicians might compose pieces inspired by the movement of the rings across the sky. The rings would become part of human culture in ways we can't fully predict, just as the moon has been part of human culture throughout our existence. The rings would also affect our view of the stars. The ring material would scatter some starlight, would block our view of certain parts of the sky, depending on where we were looking and what time of night it was. Astronomy would become more challenging. Telescopes would have to account for the rings, would need to look through gaps or accept reduced visibility in certain directions. But the rings would also create new phenomena to study. The way sunlight scattered off ring particles, creating halos and unusual optical effects. The way the ring interacted with Earth's magnetic field, possibly creating auroras of a different character than we're used to. The dynamics of how ring material evolved over time. There would be new science to do, new mysteries to unravel, all courtesy of Earth's new ring system. Let's think about what the rings would mean for Earth's appearance from space. Right now, Earth is the blue marble, that iconic image of a blue and white sphere floating in the darkness. With rings, Earth would look completely different. You'd see the blue sphere, yes, but surrounded by a flat disk of material. From certain angles, the rings would be edge-on and barely visible. From other angles, they'd be spectacular, creating a bright band around the planet. Future space missions, if we ever manage to safely leave Earth again, would send back images of Earth with rings, and those images would replace the blue marble in our collective consciousness. Earth wouldn't just be a sphere anymore. It would be a ringed world, like a smaller, rockier version of Saturn. And from other planets, if there were astronomers on Mars or Jupiter's moons watching us, they'd notice the change too. Earth would suddenly have rings visible through their telescopes. They'd wonder what happened, would speculate about the catastrophe that transformed our world. Though to be fair, Mars will eventually have rings too, when Phobos spirals inward and crosses the Roche limit, so maybe they'd understand. The rings would be temporary, on geological timescales. As we mentioned, they'd slowly spiral inward and rain down over thousands to millions of years. Eventually, they'd be gone entirely, and Earth would once again be a simple sphere. But that's so far in the future that it's almost meaningless to us. For all practical purposes, for all of human civilization's foreseeable future, the rings would be permanent. They'd outlast us, probably. Long after humanity had either rebuilt civilization or gone extinct, long after any monuments we'd built had eroded away, the rings would still be there, orbiting silently, reflecting sunlight, slowly decaying but persistent. They'd be the longest-lasting consequence of the moon's explosion, the most visible scar on our planet. And there's something both beautiful and melancholy about that. The moon, which accompanied Earth for 4.5 billion years, transformed into rings that would accompany Earth for millions of years more. Different in form, no longer a single companion, but a band of debris, but still there, still reflecting light, still shaping what Earth looks like from space. The rings would be a reminder forever of what we lost. Every time someone looked up and saw that bright band across the sky, they'd remember that it used to be the moon, that it used to be whole, that it used to rise and set and go through its phases and light the night with its pale glow. But reminders can be beautiful too. Tragic, yes, but beautiful. The rings would ensure that the moon in some form would never truly be gone. Broken, yes. Transformed, certainly, but not gone. Still there. Still part of Earth's system, still visible every night. And maybe, in some distant future when humanity had recovered from the catastrophe, when we'd rebuilt and adapted to life under rings, people would look up and see not just destruction, but also continuity. The moon wasn't lost, it was changed, and it was still ours, still part of our world, still lighting the darkness in a new way. That's the thing about rings. They're beautiful and deadly, temporary and long-lasting, a consequence of disaster and a wonder to behold. They'd change Earth forever, but they'd also connect us to our past, to the moon that used to be, to the catastrophe that remade our sky. Living under rings would be different, harder in many ways, more dangerous, more constrained, but also beautiful, also wondrous, also a daily reminder that we live in a universe of constant change, where even our most constant companions can be transformed in an instant, and what remains can be both terrible and magnificent. We've talked about the violence, the explosion, the bombardment, the rings. Now let's talk about something quieter, but equally profound. Something that happens not with a bang, but with a gradual stillness. The tides stop. Well, not entirely, that's not quite accurate. The sun still creates tides and the sun isn't going anywhere, but solar tides are only about 1/3 as strong as lunar tides, so what we'd experience is a dramatic reduction in tidal range. Places that used to see the water rise and fall by several feet twice a day would now see it rise and fall by maybe a foot. Places with extreme tides, like the Bay of Fundy, where tides can exceed 50 feet, would see them reduced to a fraction of that. The ocean wouldn't become completely static. It would still move, still have currents, still respond to wind and temperature differences, but that twice-daily rhythm of water rising and falling, that ancient pulse that's been happening for billions of years, would fade to barely perceptible. Let's start with what would happen immediately, because the interesting thing about tides is that they don't stop instantly when the moon disappears. Water has momentum. The ocean is an enormous mass, and it doesn't just suddenly become still. When the moon exploded and its gravitational influence vanished, the water would continue moving in its tidal patterns for a while, gradually slowing down as friction and other forces dissipated the energy. Over the course of days and weeks, the tidal range would decrease. Sailors and coastal residents would notice that high tide wasn't quite as high as usual. Low tide wasn't quite as low. The difference would be subtle at first, but it would compound with each cycle. The ocean would be winding down like a pendulum slowly coming to rest. And then the new equilibrium would establish itself. The sun's gravity would continue to pull on the oceans, creating small tides. But without the moon's contribution, these solar tides would be weak. The familiar rhythm of 2 high tides and 2 low tides per day would still occur technically, but the difference between high and low would be minimal in most places. The intertidal zone, that strip of coast between high and low tide, would effectively disappear in many places. Areas that were underwater twice a day and exposed to air twice a day would become either permanently wet or permanently dry, depending on where exactly they fell in the new reduced tidal range. And this would be catastrophic for intertidal ecosystems. Let's think about what lives there. Barnacles, which attach to rocks and filter food from the water when the tide is in, then close up tight when the tide is out mussels, which do something similar. Sea anemones, which capture small fish and invertebrates in their tentacles when submerged. Crabs that scuttle around tide pools, seaweeds that are adapted to regular exposure to both water and air. All of these organisms are specifically adapted to handle the daily transition between wet and dry. They've evolved over millions of years to thrive in this challenging environment, and suddenly that environment would no longer exist. The upper parts of the intertidal zone would become permanently dry. The organisms there would die of desiccation. The lower parts would become permanently submerged. Organisms adapted to periodic air exposure would struggle or die. Some species might be able to adapt. Life is resilient after all. But adaptation takes time, usually many generations. And the change would be happening over weeks and months, not the thousands or millions of years that evolution typically requires mass die-offs would be inevitable. The smell along coastlines would be particularly unpleasant for a while. Millions of dead barnacles and mussels and other organisms rotting in the sun or underwater. The first spring and summer after the moon exploded would not be a good time to visit the beach. But beyond the immediate die-off, there would be longer-term consequences for coastal ecosystems. The intertidal zone is remarkably productive. It supports an enormous amount of life for its relatively small area. Many fish species use tide pools as nurseries for their young. Shorebirds time their migrations to coincide with tides, arriving when the mudflats are exposed and full of small invertebrates to eat. With the intertidal zone gone, these species would lose critical habitat. Fish would have fewer places to spawn and raise young. Shorebirds would find less food available. The impacts would ripple through the food chain, affecting species that never directly depended on tides but fed on things that did. Let's talk about what happens in estuaries, where rivers meet the ocean. These are some of the most productive ecosystems on Earth, and tides play a crucial role in how they function. When the tide comes in, seawater pushes up into the estuary, mixing with fresh water from the river. This creates a brackish environment, partially salty, and a constant exchange of nutrients and organisms between the river and ocean. When the tide goes out, the river water flows more freely toward the ocean. This regular mixing, this back and forth, helps maintain the health of the estuary. It flushes out pollutants, brings in oxygen, circulates nutrients. It's like the estuary is breathing, and tides are the mechanism. Without strong tides, estuaries would become more stagnant. The mixing would still happen, river water would still flow into the ocean, but it would be less vigorous, less complete. Some areas might become oxygen depleted. Others might accumulate sediment that would normally be carried away by tidal currents. The water quality would decline, and the species that depend on healthy estuaries, and there are many, would suffer. Ocean circulation would also change. Now, tides aren't the primary driver of ocean currents. Wind and temperature differences do most of that work, but tides do contribute, especially in coastal areas and in narrow straits between bodies of water. They help mix deep water with surface water. They drive currents through channels and around islands. Without strong tides, some of these currents would weaken or change character. The mixing between deep and surface waters would be less vigorous. This could affect nutrient distribution in the ocean. Deep water is often rich in nutrients, and when it's brought to the surface by tidal mixing, it supports phytoplankton growth. Less mixing means potentially less productivity in some coastal areas. The Gulf Stream and other major ocean currents would likely continue largely unchanged. They're driven more by wind and the Earth's rotation than by tides. But smaller-scale circulation patterns, particularly in coastal regions, would be affected. Let's think about what this means for human activities. For most of human history, tides have been a fact of coastal life. Sailors learned to work with them, entering harbours at high tide when there was enough water depth, leaving at high tide to avoid running aground. Coastal cities were built with tides in mind, ports and harbours designed to accommodate the rising and falling water. With tides greatly reduced, some of this infrastructure would need to be rethought. Harbours designed for large tidal ranges might find their docks and piers at the wrong height. Ships that relied on high tide to enter shallow harbours might find themselves unable to get in or out. Tidal power plants, which generate electricity from the movement of tidal water, would stop working entirely. On the other hand, some things would become easier. Navigation in shallow waters would be more predictable without strong tides. The risk of running aground would decrease. Coastal flooding from extreme high tides would become less of a concern, though of course we'd have bigger problems to worry about with the meteor bombardment and climate changes. Fishing industries would be affected. Many commercial fishing operations time their activities to the tides. Certain fish are easier to catch at certain tidal stages. Shellfish harvesting depends on low tide to access beds that are normally underwater. These practices would need to change, and in the chaos following the moon's explosion, many fishing communities would struggle to adapt. Let's talk about coral reefs, because they'd be affected too. Corals are animals that build calcium carbonate structures, creating the complex reef ecosystems that support tremendous biodiversity. And many corals spawn according to the lunar cycle. They release eggs and sperm into the water on specific nights relative to the full moon. This spawning synchronization is important. By all spawning at once, corals increase the chances that eggs and sperm will meet in the vast ocean. It's a reproductive strategy that depends on having a reliable signal, the moon's phase, that all corals can detect and respond to. Without the moon, this synchronization would be lost. Some corals might continue spawning based on other cues, water temperature, day length, but the coordination would be disrupted. Reproduction success would likely decline. Over time, coral reefs would struggle to maintain themselves, adding to the many other stresses they already face from ocean acidification and warming. Sea turtles, too, would be affected. Many sea turtle species nest on beaches during specific moon phases. They use the moon as a navigation tool, both to find beaches and to orient themselves when hatchlings emerge and head for the ocean. Baby sea turtles, hatching at night, instinctively crawl toward the brightest horizon, which is normally the ocean reflecting moonlight or starlight without the moon, and with coastal areas probably dark due to destroyed infrastructure, navigation would become more difficult. Many marine species spawn or migrate according to lunar cycles. The Grunion runs in California, where fish literally beach themselves to lay eggs in the sand, a time to spring tides, the highest tides of the month. Countless other fish species spawn on lunar schedules. Crabs migrate. Even some plankton species have lunar rhythms in their behavior. All of these would be disrupted. Some species might find alternative cues. Others might lose their timing entirely. The ocean's biological rhythms, which have been synchronized to the moon for hundreds of millions of years, would be thrown into disarray. There's also something less tangible, but no less real, the loss of predictability. For all of human history, tides have been one of the most predictable natural phenomena. You could calculate tide times years in advance with great accuracy. Sailors relied on tide tables. Coastal communities planned their activities around tidal schedules. There was comfort in that predictability, in knowing exactly when high tide would occur. With the tides greatly reduced, that predictability becomes less important because the tides matter less, but the loss would still be felt. It's one more way in which the natural world, which we depend on for so much, would become fundamentally different. Let's consider the long-term implications. The tidal friction that's been slowing Earth's rotation and making days longer would essentially stop. We talked about this earlier, but it's worth emphasizing. Earth's rotation is currently being slowed by tidal interactions with the Moon. About 1.7 milliseconds are added to each day every century. Without the Moon, this braking force disappears. Earth's rotation would actually speed up slightly. Remember conservation of angular momentum from our earlier discussion, but more importantly, the long-term trend would reverse. Instead of days slowly getting longer, they'd stay roughly the same length, or possibly get very slightly shorter over geological time as other factors come into play. This is a subtle change, but over millions of years, it would mean a significantly different world. If Earth still exists in 1 billion years, which is a big if considering everything else we've discussed, it might have shorter days than it does now, rather than the longer days it would have had if the Moon had remained. The ocean would also respond to the loss of tidal mixing in ways that would take decades or centuries to fully manifest. Ocean chemistry would shift, nutrient cycles would change. The distribution of marine life would reorganize around new patterns of water movement and nutrient availability. Some areas might become more productive as different processes take over the role tides used to play. Other areas might become less productive. The ocean is a complex system, and changing one major input, tidal energy, would have cascading effects throughout the system. Coastal wetlands and salt marshes would be affected too. These ecosystems often depend on tidal flooding to deliver nutrients and remove excess salt. Without regular tidal flooding, salt might accumulate in the soil, making it harder for plants to survive. Some marshes might transition to different types of ecosystems, or might be lost entirely. And there would be cultural losses. For thousands of years, humans have organized their understanding of the ocean around the tides. We've created calendars based on them, told stories about them, built technologies to harness them. Tidal mills have been grinding grain and pumping water for centuries. Tide prediction has been a scientific pursuit since ancient times. All of that accumulated knowledge would suddenly become less relevant. Tide tables would still be published, but the entries would be small, the differences negligible. The tidal power industry would collapse overnight. The romance of tides, the poetry of the ocean's breathing, would fade into memory. Future generations would learn about tides as a historical phenomenon. Once, the ocean used to rise and fall by several feet twice a day. It was caused by the moon, which used to orbit Earth before it exploded. It would seem as strange to them as many things about the pre-moon explosion world would seem strange. But the ocean would continue. It would find new equilibriums, new patterns. The water would still move, still flow, still support life, just differently, just quieter in some ways, more chaotic in others. The tides wouldn't truly stop. The sun would ensure that. But they'd fade to a whisper of what they once were. And perhaps there would be people, coastal dwellers, sailors, marine biologists, who would miss them, who would remember when the tides were strong, when you could watch the water rise and fall with predictable regularity, when the moon pulled at the oceans and the oceans responded, creating one of nature's most reliable and most ancient rhythms. The stopping of the tides wouldn't be the most dramatic consequence of the moon's explosion. It wouldn't kill as many people as the meteor bombardment. It wouldn't change the sky as visibly as the rings. But it would be profound nonetheless. It would be the loss of something that had been constant for billions of years, something that shaped evolution and ecosystems and human culture. And in the quiet of a harbour where the water barely moves anymore, where the dock pilings show no waterline variation, where the boats float at the same level hour after hour, day after day, you might feel that loss. The absence of something you never fully appreciated until it was gone. The ocean would be different, still beautiful, still vast, still mysterious, but without its breathing, without its twice-daily rhythm, something essential would be missing, something that connected us to the moon, to geological time, to the ancient past when life first emerged from the sea. The tides would fade into history, into memory, into the list of things we lost when the moon exploded, and the ocean would continue its new, quieter existence, waiting for whatever comes next. We've explored the immediate catastrophes, the bombardment, the rings, the stopping of the tides. Now we need to talk about something that happens more slowly, something that wouldn't be noticeable for years or even decades, but would ultimately be one of the most profound consequences of losing the moon. Earth's axial tilt would become unstable. Currently, Earth is tilted at about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is why we have seasons. When the northern hemisphere is tilted toward the Sun, it's summer there and winter in the southern hemisphere. 6 months later, when the southern hemisphere is tilted toward the Sun, the seasons reverse. It's an elegant system, and it's been remarkably stable for hundreds of millions of years. But it's not stable on its own. Earth's tilt wobbles slightly. There's a natural oscillation between about 22.1 and 24.5 degrees that takes 41,000 years to complete. This is called obliquity variation, and it's part of what drives ice age cycles. But these are small variations, predictable, manageable. Life can adapt to them. The reason our tilt is so stable, the reason it stays within that narrow range, is the moon. The moon's gravity acts on the equatorial bulge of Earth. Earth is slightly fatter at the equator than at the poles due to its rotation, and this gravitational interaction creates a stabilizing torque. It's like a gyroscope being held steady by an external force. Without the moon, that stabilizing force disappears, and Earth's tilt would begin to wander. Not immediately. That's important to understand. In the first years after the moon exploded, Earth's tilt would remain at roughly 23.5 degrees. You wouldn't notice any change. The seasons would continue as normal. Summer would still be summer. Winter would still be winter. For all practical purposes, things would seem stable. But over thousands of years, the tilt would begin to drift. It would be influenced by the gravitational pull of other planets, particularly Jupiter and Saturn, by the distribution of mass in Earth's crust. Mountains and ocean basins create slight asymmetries, by various orbital factors that are usually counterbalanced by the Moon's stabilizing influence. Without that stabilizing influence, these factors would compound. The tilt might increase to 25 degrees, then 26, then more, or it might decrease, moving toward 20 degrees, then lower. The direction isn't as important as the fact that it would change, and the changes would be unpredictable on timescales relevant to civilization or evolution. We can look at Mars to see what happens to a planet without a large stabilizing moon. Mars has 2 moons, Phobos and Deimos, but they're tiny, barely more than captured asteroids. They provide essentially no stabilizing influence on Mars's rotation, and as a result, Mars's axial tilt varies wildly over millions of years. Scientists studying Mars's geological history have found evidence that its tilt has swung from as low as 15 degrees to as high as 45 degrees or more. Some models suggest it might have even reached 60 or 70 degrees in the distant past. This creates dramatic climate variations. Sometimes the poles are nearly perpendicular to the sun's rays, experiencing extreme seasons. Sometimes they're more aligned, creating milder seasonal variations but fundamentally different climate patterns. Earth would face the same instability. Our tilt could eventually swing to extreme values, maybe 40 or 50 degrees, possibly higher, or it could drop to nearly zero, and these changes would happen on timescales of thousands to millions of years. Let's think about what different axial tilts would mean for Earth's climate. Start with our current 23.5 degrees. This gives us moderate seasons. The difference between summer and winter is noticeable, but not extreme in most places. The tropics are warm year-round, the poles are cold year-round, the temperate zones experience pleasant variation. Now imagine the tilt increases to 40 degrees. Suddenly, seasons become much more extreme. Summer in the northern hemisphere would see the North Pole tilted far toward the sun, receiving nearly constant daylight and significant heating. Winter would see it tilted far away, experiencing long darkness and severe cold. The seasonal variation would be far more dramatic than what we experience now. At the equator, things would become weird. During summer in one hemisphere, the sun would pass nearly overhead, but would dip significantly during winter. The tropics, currently the most stable climate zone, would develop seasons. Meanwhile, the poles would experience extreme swings, from receiving significant sunlight during summer to complete darkness during winter. Or imagine the tilt decreases toward zero. At zero tilt, Earth would have no seasons at all. The sun would always be directly overhead at the equator and always at the horizon at the poles. The tropics would be permanently hot. The polar regions would be permanently frozen. The temperate zones, where most of human civilization currently exists, would have constant climate, neither warm nor cold, with minimal variation throughout the year. This might sound pleasant, but it would completely reshape where life could exist. Without seasonal temperature variations, many species that depend on seasonal cues for migration, hibernation, or reproduction would struggle. Plants that need winter dormancy periods would have problems. The entire ecology of temperate regions would be disrupted. And remember, Earth's tilt wouldn't stabilize at any one value. It would continue to wander. So you might have a few thousand years at 40 degrees, then a few thousand years at 25 degrees, then down to 15 degrees, then up to 50 degrees. The climate would be constantly shifting on timescales too fast for evolution to keep up, but too slow for any individual human to notice. Well, not quite. Let's talk about what you'd notice during a period of significant tilt change. Say the tilt is increasing from 23.5 degrees to 30 degrees over the course of 10,000 years. That's a change of 6.5 degrees over 10,000 years, or about 0.00065 degrees per year. You wouldn't notice this in your lifetime, not even close. Even over several generations, the change would be too subtle to detect without precise astronomical measurements. But over centuries, patterns would emerge. Summers would gradually become more intense. Winters would become harsher. The growing season in temperate regions would shift. Ice ages would become more likely, as the increased tilt creates more extreme winters that allow ice sheets to grow. Civilizations might adapt, might migrate as the climate changed, but they'd be dealing with constant, unpredictable climate change on top of all the other challenges of living in a post-moon explosion world. Agriculture would become increasingly difficult, as you couldn't rely on climate patterns remaining stable even across generations. The ice ages and warm periods that Earth has experienced throughout its history would become more chaotic. Currently, ice age cycles are driven partly by those small variations in Earth tilt, the 41,000-year cycle we mentioned earlier, but those variations are predictable. The Milankovitch cycles, as they're called, can be calculated far into the future. We know when the next ice age should occur, roughly speaking. Without the moon, these cycles would become unpredictable. You couldn't forecast ice ages thousands of years in advance because you couldn't predict what the tilt would be. Climate would become fundamentally chaotic on geological timescales. Let's think about what this means for life. Life is remarkably adaptable, certainly. It's survived 5 major mass extinctions and countless smaller crises. But life adapts through evolution, and evolution requires time and stability. You need enough generations for beneficial mutations to arise and spread through populations, and you need environments that are stable enough that those adaptations remain useful. With a wandering axial tilt, environments would be constantly changing. A species perfectly adapted to the climate at 25 degrees tilt would find itself poorly adapted when the tilt reached 35 degrees. It would either need to migrate to a new climate zone that matched its adaptations, or it would need to evolve new adaptations, or it would go extinct. Some species would manage this, the highly adaptable generalists that can survive in a wide range of conditions. But specialists, organisms finely tuned to specific climate conditions, would struggle. Biodiversity would likely decrease over millions of years as the constant climate instability filtered out all but the most flexible species. Complex ecosystems might become less complex. Food webs might simplify. The amazing diversity of life we see on Earth today, rainforests with thousands of species, coral reefs with intricate interdependencies, temperate forests with layered complexity, these require stability to develop. Constant upheaval would favor simpler, more resilient ecosystems. And this might be one of the most profound long-term consequences of losing the moon. Not the immediate catastrophe of the meteor bombardment, but the long, slow degradation of Earth's ability to support complex life. The transformation of Earth from a stable biosphere capable of producing and sustaining tremendous diversity into a less stable world where only the hardiest, most adaptable organisms could persist. We can imagine a future millions of years after the moon exploded, where Earth has gone through multiple wild swings in axial tilt, where the climate has oscillated between extremes, where the only surviving life consists of microbes, insects, and a handful of hardy plant and animal species capable of surviving anywhere from the equator to the poles in conditions ranging from tropical to glacial. It wouldn't be a dead planet. Life would persist, but it would be a diminished planet, a simpler planet, a planet that had lost the gift of stability that allowed complex life to flourish. Of course, this is a very long-term consequence. On timescales of decades or even centuries, the wobbling wouldn't matter much. Humanity, if it survived the bombardment and adapted to life under rings and without tides, could potentially thrive for thousands of years before axial instability became a serious problem. But eventually it would matter. Eventually the climate would shift enough to cause problems that couldn't be ignored. And unlike many climate changes we might face, this one would be truly beyond our control. We can reduce greenhouse gas emissions, can adapt to rising sea levels, can manage many of the climate challenges we've created for ourselves, but we can't stabilize Earth's axial tilt. Not without the moon. Well, maybe we could. This is getting into the realm of very speculative future technology, but theoretically, a sufficiently advanced civilization might be able to create an artificial moon launch enough mass into the right orbit, and you could recreate the stabilizing influence the natural moon provided. It would need to be quite massive, probably at least a significant fraction of the original moon's mass, and getting it into the right orbit would be an enormous engineering challenge. Or you could use active systems, satellites or stations that use thrusters to apply stabilizing forces to Earth's rotation. This would require constant energy input and would be difficult to maintain over geological timescales, but it's not impossible in principle. But realistically, these solutions would be beyond any near-future human technology. For practical purposes, the wobbling would be something we'd have to live with, something we'd have to adapt to or eventually flee from. This raises an interesting question. Would the axial instability eventually make Earth uninhabitable? Not in the short term, certainly. Millions of years of climate chaos would be challenging for civilization and difficult for complex ecosystems, but life in general would persist. Earth has been through worse and recovered. But over tens or hundreds of millions of years, it's hard to say. Mars, with its unstable axial tilt, is not a lush biosphere. Though to be fair, Mars has many other problems. Thin atmosphere, weak magnetic field, small size. The unstable tilt is just one of many factors that make it inhospitable. Earth has advantages Mars doesn't have. We're larger, with stronger gravity to hold onto our atmosphere. We have active plate tectonics that recycle carbon and regulate climate over long timescales. We're in a better position in the habitable zone. Even with a wobbling tilt, Earth would likely remain more hospitable than Mars for a very long time. But it would be a degraded Earth, a planet that couldn't quite maintain the stable, comfortable conditions that allowed complex life to evolve and thrive. A planet in slow decline, not toward death, but toward simplicity, toward resilience at the cost of diversity. And all because we lost the moon, all because that stabilizing influence, that gravitational gyroscope was removed. The immediate catastrophes, the bombardment, the tsunamis, the societal collapse, those would be terrible, but the slow wobbling, the gradual descent into climate chaos, that might ultimately be the most profound consequence of all. It's a sobering thought. The moon doesn't just light our nights and create our tides. It holds our planet steady. It gives us the gift of stability, of predictable seasons, of a climate that varies on timescales slow enough for life to adapt. Without it, Earth would still be Earth. It would still orbit the sun, would still have oceans and continents and an atmosphere. But it would wobble, and that wobble, subtle as it would seem in any human lifetime, would compound over geological time into something significant. Something that would reshape what it means to live on this planet. Something that would make Earth a less welcoming place for complex life, including us. The wobbling Earth is a slow-motion catastrophe, one that takes millions of years to fully unfold. but it's no less real for being slow. And it's a reminder that the moon's gifts aren't just the obvious ones, light and tides, but also this subtle, invisible gift of stability, the gift of a planet that doesn't wobble too much, a planet where seasons remain predictable across deep time, a planet capable of supporting the kind of rich, complex biosphere we're part of. Losing that gift wouldn't doom Earth, but it would diminish it, slowly and inexorably, for as long as Earth exists. And that's a kind of loss that's hard to fully comprehend, because it plays out on timescales we're not built to think about, but it's real nonetheless. And it would be the moon's most lasting legacy, not just what was lost immediately, but what would slowly unravel over the eons that followed. Here's something that might seem counterintuitive at first. When the moon explodes and stops pulling on Earth's tides, when that constant tidal friction disappears, Earth doesn't slow down. It speeds up. Not by much, and not immediately, but the trend reverses. Days get shorter rather than longer. Let's talk about why this happens, because it's a beautiful piece of physics that connects rotation, tides, and the conservation of angular momentum. Currently, Earth is rotating once every 24 hours. That's our day, the fundamental unit of time we base our lives around. But this hasn't always been the case. Early in Earth's history, days were much shorter. About 4 billion years ago, a day might have been only 6 hours long. The planet was spinning much faster. Over billions of years, tidal friction has been slowing Earth down. The moon pulls on Earth's tidal bulges, those two bulges of water we talked about earlier, one facing the moon and one on the opposite side. But Earth is rotating faster than the moon, orbits, so the tidal bulges are slightly ahead of the moon in Earth's rotation. The moon's gravity pulls back on these bulges, creating a drag force that slows Earth's rotation. This lost rotational energy doesn't disappear. Energy is conserved in the universe. Instead, it's transferred to the moon's orbit, causing the moon to slowly spiral outward. Earth spins down, the moon moves out, and the total angular momentum of the Earth-Moon system remains constant. It's elegant, really. Earth trades some of its spin for the moon's distance. This process has been happening for billions of years. Days have been getting longer at a rate of about 1.7 milliseconds per century. That's not much. You'd never notice it in a human lifetime, but over geological time, it adds up. A day 620 million years ago was about 22 hours long. A day 900 million years ago might have been 18 hours. The trend has been consistently toward longer days. But when the moon explodes, when it's no longer there to create tidal friction, this braking force disappears. The drag on Earth's rotation is removed, and while Earth doesn't suddenly start spinning faster, objects don't spontaneously change their rotation speed, the process of slowing down stops. Actually, there's a bit more to it than that. When the moon's mass is redistributed, some of it falling to Earth, some forming rings, some escaping into space, the angular momentum of the system changes. Some of that angular momentum gets transferred back to Earth. It's like a figure skater pulling their arms in and spinning faster, except in this case, it's Earth pulling in debris from its former moon. The net effect would be a slight increase in Earth's rotation rate. Days would become shorter. Not by hours, we're talking about minutes at most in the immediate aftermath. But the important thing is the reversal of the trend. Instead of days getting longer over millions of years, they would stay roughly constant or possibly get shorter. Let's think about what a slightly shorter day would mean. Say the day drops from 24 hours to 23 hours and 55 minutes. That's a 5-minute reduction, which is probably on the high end of what you'd actually see, but let's use it as an example. Your circadian rhythm, your internal biological clock, is set to roughly a 24-hour cycle. It's not exactly 24 hours, actually. Studies of people living in environments without time cues show that the natural human circadian rhythm runs slightly longer than 24 hours, maybe 24.2 hours on average. We reset it daily by exposure to light and social cues, synchronizing our internal clock to the external day-night cycle. A 5-minute shorter day wouldn't break this system, but it might make it slightly less comfortable. Your body wants to run on its natural cycle, and now the external day is even shorter than the 24 hours you were already compressing yourself into. People might feel slightly more rushed, slightly more tired. Sleep patterns might shift. But honestly, 5 minutes is small enough that most people would adapt without major issues. We already deal with much larger disruptions: jet lag, daylight saving time, shift work. A 5-minute change would be barely noticeable compared to those. The bigger issue would be the reversal of the long-term trend. For billions of years, the universe has been giving us more time, longer days, more hours to work with, and now that gift would stop. Days would stay the same length, or possibly get shorter over time if other factors came into play. This might seem like a minor concern given everything else going on, and to be fair, it is relatively minor compared to the meteor bombardment and the climate instability. But there's something psychologically significant about it. The universe has been, in a sense, on our side. It's been giving us more time, slowly but surely, and now it's not. Let's talk about biological impacts beyond just human circadian rhythms. Many organisms have internal clocks synchronized to the 24-hour day. Plants open and close their flowers on daily schedules. Some open at dawn, others at dusk. Nocturnal animals become active as darkness falls. Diurnal animals wake with the light. These rhythms are driven by internal clocks that are entrained, synchronized to the day-night cycle. And these clocks are usually fairly flexible. They can adapt to small changes in day length. We know this because day length varies throughout the year anyway. Days are longer in summer than in winter at any latitude away from the equator. So a small change in the average day length would probably be manageable for most organisms. Plants would adjust their flowering times, animals would shift their activity patterns. It wouldn't be seamless, and some species might struggle more than others, but it wouldn't be catastrophic. What's more interesting is thinking about what happens over millions of years if days continue to get shorter. Right now, the evolutionary trend for the past few billion years has been toward longer days. Life has been adapting to gradually increasing day length. Organisms that could handle longer days had a slight advantage. With the trend reversing, evolution would now favor organisms that can handle shorter days. This is a subtle, selective pressure, but over enough time, it would shape life. Maybe nocturnal animals would become less common, since there'd be less night time to work with. Maybe photosynthetic organisms would evolve slightly more efficient mechanisms to make use of the daylight they have. Or maybe it wouldn't matter much at all. 5 minutes, even accumulated over millions of years into an hour or two, is still a relatively small change. Life is adaptable. It survived far more dramatic environmental changes. Let's think about weather patterns, because Earth's rotation affects weather in interesting ways. The Coriolis effect, the apparent deflection of moving objects due to Earth's rotation, is what creates the swirling patterns of hurricanes and the curving paths of ocean and air currents. The strength of the Coriolis effect depends on the rate of rotation. Faster rotation means stronger Coriolis effect. So with Earth spinning slightly faster, weather patterns would be slightly affected. Hurricanes might spin more tightly. The jet streams might shift position slightly. Ocean gyres might circulate a bit more vigorously. Again, we're talking about small effects. A 5-minute reduction in day length would increase the rotation rate by about 0.3%. The Coriolis effect would strengthen by a similar percentage. This is not enough to fundamentally change weather patterns, but it might make storms slightly more intense, might shift climate zones by small amounts. Over millions of years, if the rotation continued to speed up, the effects would compound. Weather would become more energetic. Storms would be stronger. The bands of different climate zones might compress closer to the equator. But these are very long-term consequences, the kind of thing that would unfold over geological time. There's also the question of what other factors might affect Earth's rotation. The Moon's tidal friction is the main thing that's been slowing us down, but it's not the only factor. The Sun creates small tidal effects. The redistribution of mass on Earth's surface, ice sheets forming and melting, for example, affects rotation slightly. Even the motion of the atmosphere and oceans transfers angular momentum to and from the solid Earth. Without the dominant influence of lunar tidal friction, these other factors would become relatively more important. Earth's rotation would be influenced by a complex interplay of solar tides, mass redistribution, and atmospheric effects. The day length might fluctuate slightly over time rather than following a steady trend. This unpredictability would make things interesting for astronomers and timekeepers. Right now, we can calculate Earth's rotation very precisely and predict how it will change. We know that atomic clocks which keep perfect time will gradually drift out of sync with Earth's rotation. We add leap seconds occasionally to keep our clocks aligned with the planet's actual spin. Without the Moon, the drift would be different and less predictable. We'd still need leap seconds, but their timing would be harder to forecast. It's a small technical challenge, but it's representative of a larger point. Many things we take for granted about how our planet works would become slightly less predictable. Let's talk about one more consequence of Earth's changing rotation, the length of the year. A year is the time it takes Earth to orbit the Sun, about 365.25 days, but a day is the time it takes Earth to rotate once. If the length of a day changes, the number of days in a year changes too, even though the year itself, the orbital period, stays the same. Right now we have about 365.25 rotations per orbit. If days got shorter, we'd have more rotations per orbit. Maybe 365.5 days per year, or 366 days per year, depending on how much the rotation sped up. This would mess with our calendar systems, which are carefully calibrated to the current day length. We'd need to adjust, maybe add an extra day to the calendar, maybe redefine how long a day is, decoupling the word from Earth's actual rotation period, and making it a fixed length of time instead. This is actually something we've already done in a sense. Our official day is defined in terms of atomic time, not Earth's rotation, specifically because Earth's rotation isn't perfectly uniform. But for most of human history, a day meant one rotation of Earth, and that was that. Changing that definition would be philosophically strange, even if it was practically necessary. There's something almost melancholy about the idea of faster days, not because the change itself is harmful, it's not really, but because it represents another way in which our connection to cosmic time would be altered. For billions of years, each day has been slightly longer than the day before. That steady, predictable trend connected us to the deep time of geology, to the gradual evolution of the Earth-Moon system. With that trend reversed or stopped, we'd lose that connection. Days would no longer be a slowly accumulating gift from the universe. They'd be static or possibly shrinking. It's a small loss in the grand scheme of everything we'd lose with the Moon's explosion, but it's a real one. And here's a thought. Every civilization that's ever existed on Earth has lived with the knowledge that days are getting longer. Ancient astronomers couldn't measure it directly, but modern science has revealed this truth. It's been a constant for all of life's history, and we'd be the first generation to experience its reversal. That's strange to think about. We'd mark the boundary. Before us, days got longer. After us, they don't. We'd live through the transition point, the moment when billions of years of one trend gives way to something different. Of course, in the chaos of everything else happening, the bombardment, the climate instability, the social collapse, this particular change would probably not be high on anyone's list of concerns. You'd worry about the rocks falling from the sky before you worried about whether your day is 5 minutes shorter. But in the long term, in the very long term, it would matter. It would be one more way in which Earth became a different place, one more severing of the connection to how things have been for billions of years. The moon has been slowing Earth down, giving us longer days for our planet's entire history. It's been a subtle gift, barely noticeable on human timescales, but profound over geological time. And when the moon exploded, when that influence disappeared, the gift would stop. Days would no longer get longer. They might get shorter, and Earth would spin through space slightly faster, slightly more alone, without its companion to gradually slow its rotation and steal that energy for its own orbit. It's a small change, but in a world where we've lost so much, the moon itself, the tides, the stable climate, even small changes feel significant. Even a few minutes matters when you're counting what remains. Let's talk about darkness. Real darkness. The kind that most people alive today have never truly experienced. The moon provides about 1/400,000th of the light that the sun does. That sounds like almost nothing, doesn't it? A tiny fraction. Negligible. But here's the thing about light and darkness. Your eyes are remarkably good at adapting to low light conditions. That tiny fraction is enough to see by, enough to cast shadows, enough to navigate a path, read a book if you're patient, recognize a face. On a clear night with a full moon away from city lights you can see quite well. Not daylight level vision, certainly. Colours fade to shades of grey, details become less sharp, but you can function. You can walk through a forest without tripping over roots. You can see a person standing 20 feet away. The world is visible. Without the moon, that changes. Night becomes truly dark, in a way most of us have never experienced. There are still stars, of course, thousands of them visible to the naked eye, more if you're far from city lights, but starlight alone is dim, much dimmer than moonlight. On a moonless night, even now, the difference is striking. Add in the loss of moonlight forever, and nights become dark in a way that's hard to describe if you've never experienced it. Well, we'd have the rings, actually. Those would reflect some sunlight, providing ring shine as we discussed earlier. Depending on the ring's density and reflectivity, this might provide more or less light than the moon did. But let's assume for the moment that the rings are sparse enough or dark enough that they don't fully replace moonlight, or that you're at a latitude where you can't see the rings well. The principle remains: nights would be darker than we're used to. This would affect nocturnal life significantly. Many species have evolved to use moonlight. Owls hunt by it. Their exceptional night vision is very good, but even owls do better with some ambient light. On completely dark nights, hunting success rates drop. Moths famously use the moon for navigation. They orient themselves by maintaining a constant angle to the moon as they fly, which works fine when the moon is 384,000 kilometers away, and its position barely changes relative to a moth's flight path. But this same strategy fails catastrophically around artificial lights, which is why moths spiral into flames and light bulbs. They're trying to maintain that constant angle, but with a close light source, maintaining a constant angle means flying in a tightening spiral. Without the moon, moths would lose their primary navigation reference. Some might adapt to use stars instead, though that's more complex. Stars appear to rotate across the sky, so you can't use a single star. The way you can use the moon, moths might become less successful navigators, might evolve different strategies, or might decline in numbers. Nocturnal primates, species like lorises and tarsiers that are active at night, rely on moonlight to move through trees and hunt insects. They have large eyes adapted for low light, but even large eyes need some light to work with. Truly dark nights would make their lifestyle more challenging. They might shift their activity patterns, becoming crepuscular, active at dawn and dusk, rather than truly nocturnal. Let's talk about sea turtles, because their relationship with the moon is particularly poignant. Sea turtles nest on beaches, and many species time their nesting to specific lunar phases. The females come ashore during high tides associated with full moons, dig nests in the sand, lay their eggs, and return to the ocean. When the eggs hatch, typically about 60 days later, the tiny turtles emerge from the sand and instinctively crawl toward the brightest part of the horizon. Naturally, this would be the ocean reflecting moonlight or starlight. It's a simple and usually reliable navigation strategy. The ocean is bright, the land is dark, crawl toward brightness. But this strategy fails in the modern world, where coastal development means artificial lights often make the land brighter than the ocean. Hatchlings crawl toward buildings instead of water, and most die before finding the ocean. It's a tragedy of evolved instincts meeting changing environments. Without the moon, the strategy would fail for a different reason. Neither the ocean nor the land would be particularly bright. Hatchlings might crawl in random directions, might take longer to find the ocean, might have lower survival rates. The sea turtle populations, already stressed by human activity and climate change, would face another challenge. Coral spawning would also be affected. We touched on this earlier, but it's worth elaborating. Many coral species spawn on specific nights relative to the lunar cycle, often a few days after the full moon. The timing is crucial because all the corals of a species need to spawn simultaneously to maximize the chances that eggs and sperm will meet in the vast ocean. Without lunar cues, this synchronization would break down. Some corals might spawn based on other cues, water temperature, day length, but the coordination would be less perfect. Reproductive success would decline. Coral reefs, already stressed by warming oceans and acidification, would face yet another pressure. But let's shift from ecology to culture, because humanity's relationship with the moon runs deep. The moon has been part of human consciousness for as long as there have been humans. Every culture on Earth has moon mythology, moon calendars, moon-inspired art. The word month comes from moon. It originally meant one lunar cycle, the time from new moon to new moon. Many cultures still use lunar calendars. The Islamic calendar is purely lunar, with each month beginning when the first crescent of the new moon is visible. The Jewish and Chinese calendars are lunisolar, combining lunar months with solar years, through careful calculation and occasional extra months. Without the moon, these calendar systems would become historical curiosities. The Islamic calendar would need to be redefined. Based on what? Arbitrary 29 to 30-day periods with no celestial reference? The entire structure of how these cultures mark time would be disrupted. And there's the poetry of it, the romance. How many love songs mention the moon? How many poems describe moonlight on water or a lover's face in moon glow? Moon river, blue moon, fly me to the moon, moon shadow, Entire genres of music would suddenly be singing about something that no longer exists. Children born after the explosion would learn about the moon the way we learn about dinosaurs, as something that used to exist, that's gone now, that we can only know through records and stories. They'd see pictures and videos, would read about how it looked, how it moved across the sky through its phases, but they'd never see it themselves. There's something deeply sad about that. The moon has been humanity's companion since before we were human. Our ancestors looked up at it. Every person who has ever lived has seen it. And then, suddenly, a generation that hasn't. A permanent break in the continuity of human experience. The moon has inspired scientists too, not just poets. Lunar exploration was one of humanity's greatest achievements. That's one small step for man, one giant leap for mankind. The moon landings represented not just technical achievement, but a philosophical milestone. Humans leaving our planet, touching another world, proving we could do it. The moon was supposed to be our stepping stone to the solar system. We'd establish bases there, use it as a launch pad for deeper space missions. The lower gravity and lack of atmosphere make launching from the moon much easier than launching from Earth. It was going to be our gateway to the cosmos. With the moon gone, that plan disappears. Mars becomes the next closest destination, but Mars is orders of magnitude further away and harder to reach. We lose our stepping stone, our nearby target for developing space technology and learning to live away from Earth. There would be historical sites on the moon too. The Apollo landing sites, with their flags and footprints and equipment. Lunar 2 impact site, the first human-made object to reach another world. The various rovers and landers from different countries. All of this would be destroyed when the moon exploded, or would be part of the debris rain. Future archaeologists wouldn't be able to visit these sites, wouldn't be able to preserve them as monuments to human achievement. Let's think about the darkness in more practical terms. Before artificial lighting, the moon mattered enormously to human activity. Farmers would plan their work by it. Travellers would journey by it. Night markets in pre-industrial societies often coincided with full moons because that's when you had enough light to see your goods and customers. Harvest moon isn't just a romantic name. It referred to the full moon closest to the autumn equinox, which rises around sunset for several nights in a row, providing extra hours of light for bringing in crops. The hunter's moon was the next full moon, when you could hunt by moonlight as animals prepared for winter. These weren't arbitrary traditions. They were practical responses to the reality that moonlight provided usable illumination. Without it, nighttime work became much harder. You'd need torches, fires, eventually oil lamps and candles. Light sources that require fuel and effort to maintain. In the modern world, we have electric lights, so the loss of moonlight wouldn't affect practical activities as much. But there's still something about moonlight that's special. It's free. It's available to everyone. It doesn't require infrastructure or resources. On a clear night with a full moon, anyone anywhere can see well enough to walk, to read, to work if they need to. That democratic accessibility would be lost. Night vision would require either artificial light, which requires money, resources, working electrical grids, or true darkness adaptation, which works less well without any ambient light source. There's also the simple beauty of moonlight, the way it transforms landscapes, making familiar places look different, ethereal, almost magical moonlight on water, the way it creates a path of silver across waves. Moonlight through trees, dappled shadows and soft illumination. These are aesthetic experiences that have inspired artists for millennia. A world without moonlight would still have beauty, certainly. Starlight has its own quality. The rings, if bright enough, would create new kinds of light and shadow, but it would be different. Another way in which the world would be changed, diminished, made less than it was. Think about the moon's phases too, the rhythm of watching the moon grow from new to full and back again, the names we have for different phases, crescent, quarter, gibbous, full, the way the moon rises at different times depending on its phase, the surprise of seeing a daytime moon pale against blue sky. This rhythm has structured human experience of time in subtle ways. You can tell roughly what time of month it is by looking at the moon's phase. You can predict when it will rise and set. Sailors used the moon to navigate. Farmers used it to time planting. Countless cultures developed sophisticated understanding of lunar cycles. All of that knowledge would become historical, something that used to be useful, that people used to care about, that's now irrelevant because the thing it described no longer exists. And there's the werewolf mythology we joked about earlier. Every culture has stories about the moon, deities, spirits, creatures that transform under its light. The moon has been mysterious, powerful, often feminine in character, sometimes trickster-like, always significant. These stories wouldn't make sense to future generations. Why would someone transform during a full moon? What's a full moon? It's when the moon was, and then you're explaining something that doesn't exist anymore. The stories would persist, probably, the way Greek myths persist even though we don't believe in Zeus. But they'd be disconnected from any lived reality. Children born after the moon exploded would grow up in a world without moonlit nights. They'd never see the moon rise over an ocean. They'd never try to spot the man in the moon, or the rabbit pounding rice that some Asian cultures see in the lunar area. They'd never watch a lunar eclipse. They'd never experience that particular quality of light that moonlight provides. And maybe they'd be fine. Maybe they'd adapt to the darkness, or to the ring light, or to whatever the new normal became. Humans are remarkably adaptable. We can get used to almost anything. But something would be lost, something that connected every human to every other human across all of history. The shared experience of seeing the moon, of living under its light, of marking time by its phases. That continuity would be broken. The nights would be darker. Not just physically, though, they would be that, but darker in meaning, darker in possibility, darker in the sense of having lost something old and irreplaceable. And in that darkness, we'd remember what we had. We'd remember the light that used to grace our nights. We'd remember the companion that used to watch over us. We'd remember the moon, and we'd miss it, and there would be nothing we could do to bring it back. The darkness would be permanent, and we'd learn to live with it, because what choice would we have? But it would be one more way in which the world after the moon exploded would be a sadder, lonelier, darker place than the world that came before. We've explored all the ways the moon's explosion would damage, disrupt, and fundamentally change Earth. The bombardment, the rings, the climate instability, the darker nights. It's been rather bleak, hasn't it? So let's address the natural question that arises after cataloguing catastrophes. Could anything survive? Could life adapt? The short answer is yes. Almost certainly yes. Life is remarkably resilient, and Earth has been through worse. But the longer answer is more complex, and it depends on what timescale we're considering and what we mean by life. Let's start with the immediate aftermath, the first weeks and months when the meteor bombardment is at its peak. This would be, without question, a mass extinction event, comparable in severity to the asteroid impact that ended the Cretaceous period and killed the dinosaurs. Possibly worse, depending on how much moon debris actually hits Earth. Large land animals would be particularly vulnerable. They can't easily hide from impacts, they need a lot of food, and they're affected by the climate disruption that would follow the bombardment. Dinosaurs didn't all die from the direct impact of the Chicxulub asteroid. Most died from the impact winter that followed, when dust in the atmosphere blocked sunlight and temperatures dropped and food chains collapsed. We'd face something similar: the dust from multiple impacts, the fires from atmospheric heating during meteor entry, the disruption of agriculture and natural food sources. All of this would make survival difficult for large animals. Some would die from direct impacts or their immediate effects. Most would die from starvation and cold as ecosystems collapsed. But not all. Some large animals would survive. The ones in the right places at the right times, the ones that could adapt to eating whatever food remained available, the ones that got lucky. A percentage would make it through the worst of the bombardment and face the changed world that followed. Small animals would fare better. Anything that can burrow, rodents, rabbits, many insects, would have shelter from impacts. They can survive underground, protected by meters of soil and rock from all but the largest impacts. They need less food, so they can survive on whatever scraps remain. And they reproduce quickly, meaning populations can recover faster from losses. This is basically what happened after the Chicxulub impact. Large dinosaurs died, small mammals survived, then diversified into all the ecological niches the dinosaurs left empty. Given enough time, life rebounds from mass extinctions. It changes, yes. The species are different after than before. But it persists. Aquatic life would have mixed fates. Fish and marine mammals near the surface would be vulnerable to impacts and the immediate changes in ocean conditions. But the ocean is deep, and most of it would be unaffected by surface impacts. Deep-sea ecosystems, already living in permanent darkness and adapted to extreme conditions, would barely notice the moon's explosion. To them, it would just be another Tuesday. And the deep-sea hydrothermal vent communities we've mentioned several times, those would be completely fine. They don't depend on sunlight. They don't care about moonlight. Tides don't affect them at their depth. The meteor bombardment is irrelevant when you're several kilometers below the ocean surface. These ecosystems would persist, unchanged, indifferent to the catastrophe happening above. Plant life would struggle but survive. The immediate bombardment would destroy forests, would burn vegetation, would bury plants under impact debris. The impact winter that followed would reduce sunlight, making photosynthesis difficult. Many plant species would die. But plants have seeds. Seeds can survive for years, sometimes decades, waiting for favorable conditions. When the bombardment ended, when the dust settled and sunlight returned to normal levels, those seeds would germinate. New growth would emerge from the devastation. Not the same species necessarily. The survivors would be the hardy generalists, the opportunists, the species with the most resilient seeds. Over decades and centuries, vegetation would return. It might look different, simplified ecosystems rather than complex forests, more shrubland and grassland than mature woodland, but it would return. The process that turned lifeless volcanic islands into lush ecosystems over thousands of years would repeat itself across Earth. Humans would face particular challenges. We're large animals with complex needs. We need a lot of food and water. We depend on infrastructure and technology that would be destroyed or severely damaged. We're vulnerable to both the direct impacts and the secondary effects. Societal collapse, resource shortages, conflict over what remains. But humans are also remarkably adaptable. We're generalists who can eat a wide variety of foods. We're intelligent enough to plan ahead, to build shelters, to preserve resources. We cooperate in large groups, which allows us to undertake complex survival strategies. And we're distributed globally, so no single catastrophe would eliminate all populations. The survival of humanity would depend heavily on preparation and luck. If we had warning, and we would, We'd see the moon exploding and could track at least some of the incoming debris. We could prepare somewhat move populations to regions less likely to be hit, stockpile food and water, build reinforced shelters. These measures wouldn't save everyone, but they'd save some. Underground communities would have the best chances. Deep mines, cave systems, bunkers built during the Cold War and expanded for this new crisis. These could house populations safely during the worst of the bombardment. Not comfortably. You'd be dealing with crowding, limited resources, psychological stress, but alive, which is the important part. The long-term challenge would be rebuilding in a world that's fundamentally changed. No reliable tides, so coastal infrastructure would need to be completely rethought. Rings in the sky that create meteor hazards and make space travel extremely dangerous. Climate instability that would make agriculture increasingly difficult over millions of years. Darker nights that would affect everything from safety to psychology. But humans have rebuilt from civilizational collapses before. We've survived ice ages, plagues, famines, wars. We're resilient. If nothing else, we'd rebuild. Differently, probably. A civilization shaped by the reality of living under rings, of the constant low-level meteor danger, of a world without tides or moonlight. But we'd rebuild. The question of whether we'd thrive or merely survive is harder to answer. Much would depend on how much knowledge and technology we could preserve through the crisis. If we maintained industrial capacity, if we kept libraries and databases intact, if we retained the accumulated wisdom of centuries of science and engineering, we'd recover faster and more completely. If the collapse was total, if we lost most of our knowledge and had to rediscover everything from near scratch, recovery would take longer and might plateau at a lower level of technological development. It's hard to build advanced technology when you don't have reliable access to resources and have to worry about meteors falling from the sky. Let's think about adaptation on longer timescales. Over thousands and millions of years, as the climate became more unstable due to the wobbling axial tilt, life would need to evolve new strategies. The species that would do best would be the generalists, organisms that can tolerate a wide range of temperatures, that can live in many different environments, that don't depend on stable conditions. Think rats, pigeons, cockroaches, species that thrive in changing conditions, that are opportunistic rather than specialized. Specialists would struggle. Species adapted to specific temperature ranges, specific habitats, specific seasonal patterns. These would find their niches disappearing as climate wobbled. Some would go extinct. Others might evolve more flexible adaptations, becoming more generalist in the process. Biodiversity would likely decrease over time, not because mass extinction would kill everything, life would persist, as it always has, but because the constant environmental instability would favor simplicity over complexity. Complex ecosystems with intricate food webs and subtle interdependencies require stable conditions to maintain themselves. Simpler ecosystems with fewer species and more straightforward relationships are more resilient to change. This is actually similar to what we see in harsh environments on Earth now. Polar regions have less biodiversity than tropical rainforests because the harsh conditions limit which species can survive. A post-moon Earth wouldn't become as harsh as Antarctica, but the principle would be similar. Instability would act like harshness, filtering out all but the most adaptable species. But let's not be entirely pessimistic. Life is creative. Evolution finds surprising solutions. Given millions of years, new species would evolve that are specifically adapted to the new conditions, species that can handle variable climates, species that time their life cycles to ring phenomena instead of lunar phases, species that navigate by starlight rather than moonlight. The post-moon biosphere might eventually become as complex and diverse as the pre-moon biosphere, just different, filled with species that have no equivalent in our current world, adapted to conditions we've never experienced. It's hard to predict what evolution would produce given such different selection pressures. And there's something almost hopeful in that. Even in the worst-case scenario, even with the moon gone and climate unstable and countless species extinct, life would continue. It would change, would adapt, would fill empty niches with new forms. Earth would remain a living planet, not as rich as it is now perhaps, but still teeming with organisms doing what life does, surviving, reproducing, evolving. Humans specifically might face challenges to our long-term survival, not from the immediate catastrophe, we've established we'd likely survive that, but from the million-year timescale climate instability. Our civilization depends on being able to predict climate, to plan agriculture based on expected temperatures and rainfall, to build cities in places that will remain habitable. With a wobbling axial tilt, that predictability would be lost over geological time. Areas that are temperate now might become tropical or frozen depending on how the tilt evolved. Sea levels would change as ice caps grew or melted. Climate zones would shift unpredictably. We might need to become a nomadic species again, moving with climate changes rather than staying in fixed locations. Or we might need to develop technology sophisticated enough to create controlled environments, to decouple our survival from external climate entirely, essentially living in climate-controlled bubbles, whether on Earth's surface or underground or even in space. Or, and this is perhaps the most likely long-term outcome, we might leave. If we survive the initial catastrophe and rebuild enough technological capacity, we might decide that Earth, much as we love it, is no longer the best place for humanity. We might become a multi-planet species out of necessity rather than curiosity. Mars, for all its challenges, has a more predictable climate than post-moon Earth would have on million-year timescales. It's harsh, yes, but it's consistently harsh. You know what you're dealing with. Earth would be unstable, unpredictable, gradually becoming less hospitable to complex life. At some point it might make sense to move on. This is bittersweet. Earth is our home. It's where we evolved, where all of human history has taken place, where every person who ever lived was born leaving it, would be abandoning something profound, something irreplaceable. But if staying meant slow decline, if leaving meant survival and possibly even flourishing, we might choose to go. And perhaps we'd leave life behind. Terraformed Mars might eventually have its own biosphere, seeded with Earth organisms adapted to Martian conditions. We could carry life with us, spreading Earth biology across the solar system even as Earth itself became less hospitable. So could life adapt? Yes, life would survive the immediate catastrophe, would persist through millions of years of climate instability, would evolve new forms suited to new conditions, would continue being what life is, resilient, creative, persistent. Would it be the same? Number. We'd lose species, lose complexity, lose much of what makes Earth's current biosphere so remarkable. The post-moon biosphere would be diminished in many ways. Would humans survive? Probably, at least in the medium term. We're clever and adaptable enough to make it through the bombardment and rebuild some form of civilization. Long term, we'd either adapt to the instability, develop technology to overcome it, or leave through the worlds. The moon's explosion wouldn't be the end of life on Earth, but it would be the end of Earth as we know it, the end of stability, of predictability, of the delicate balance that allowed complex life to flourish. And while life would continue, would adapt, would persist. It would do so in a world that's fundamentally lesser, fundamentally changed, fundamentally diminished by the loss of its ancient companion. We've spent considerable time imagining what Earth would be like without its moon. But let's take a step back and look at the bigger picture. Let's explore the other moons in our solar system, because doing so helps us understand just how special our moon really is, and how unusual the Earth-Moon relationship is compared to what we see elsewhere. First, let's talk about how many moons there are. The solar system is, it turns out, absolutely full of them. Jupiter currently has 95 known moons. Saturn has 146. Even Mars, that small, cold desert world, has 2 moons. Mercury and Venus have none, which makes them the odd ones out among the planets. But here's the thing, most of these moons are tiny. They're captured asteroids, irregular chunks of rock measuring just a few kilometers across. They're moons in the technical sense. They orbit a planet, but they're not what we usually picture when we think of a moon. They don't dominate their planet's sky. They don't create significant tides. They barely affect their planet at all. Our moon is different. It's huge relative to Earth. The moon's diameter is about 27% of Earth's diameter, more than a quarter the size of the planet it orbits. This is an unusually large ratio. So large, in fact, that some astronomers prefer to think of the Earth-Moon system as a binary planet, rather than a planet with a satellite. No other moon in the solar system has this kind of relationship with its planet. Ganymede, Jupiter's largest moon, is actually bigger than our moon in absolute terms. It's even bigger than the planet Mercury. But compared to Jupiter, which is enormous, Ganymede is relatively small. The ratio is nothing like the Earth-Moon ratio. This matters because the size of a moon relative to its planet determines how much influence it has. Our moon is large enough to significantly affect Earth's rotation, to create strong tides, to stabilize our axial tilt. Most moons are too small to do any of these things for their planets. Let's take a tour of some of the more interesting moons in our solar system, starting with the ones closest to the Sun and working outward. Mars has 2 moons, Phobos and Deimos. Both are tiny. Phobos is about 22 kilometers across. Deimos is even smaller at about 12 kilometers. They're almost certainly captured asteroids, irregular in shape, covered in craters and dust. From Mars's surface, Phobos would look like a bright star, not a disk like our moon does. Deimos would be even less impressive. But Phobos is interesting for a rather dark reason. It's doomed. Phobos orbits very close to Mars, only about 6,000 kilometers above the surface, and it's slowly spiraling inward due to tidal forces. In about 50 million years, Phobos will cross Mars's Roche limit, the point where tidal forces overcome its own gravity, and it will be torn apart. Mars is going to get rings, temporary rings, lasting perhaps tens of millions of years before they either fall to the surface or disperse into space. In a sense, Mars is going to experience a less catastrophic version of what we've been imagining for Earth. Its moon will be destroyed, though by tidal forces rather than explosion, and the debris will form rings. The difference is that Phobos is so small that its destruction won't have much impact on Mars. There will be no significant meteor bombardment, no loss of tidal stability, because Phobos wasn't creating those effects in the first place. It's almost a non-event, astronomically speaking. A small moon breaking apart to form small rings around a planet that barely noticed it was there. Moving outward to Jupiter, we find a completely different situation. Jupiter has 4 large moons, Io, Europa, Ganymede and Callisto, discovered by Galileo in 1610. These are substantial worlds in their own right, each with its own character and geology. Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by sulfur and silicate volcanoes driven by tidal heating from Jupiter's gravity. The tides on Io aren't ocean tides. Io doesn't have oceans, but tides in the solid body of the Moon itself, which flex and generate heat through friction. Europa is perhaps the most intriguing moon in the solar system for astrobiologists. Beneath its icy surface lies a global ocean of liquid water, kept warm by tidal heating, similar to Io's. This subsurface ocean might harbour life, simple organisms living in the dark, fed by chemical energy from hydrothermal vents, similar to the deep-sea vent communities on Earth. If Europa does have life, it would be completely unaffected by anything happening to the Sun or other planets. It lives under kilometres of ice, in an ocean heated by tidal forces from Jupiter. The explosion of Earth's moon wouldn't change Europa's situation at all. It's a reminder that life, if it exists elsewhere in the solar system, might be independent of the Sun in ways Earth life isn't. Ganymede, the largest moon in the solar system, is bigger than Mercury. It has its own magnetic field, something very few moons can claim. It too might have a subsurface ocean. Callisto, the outermost of the Galilean moons, is heavily cratered and ancient, its surface recording billions of years of impacts. These moons are fascinating worlds, but none of them dominate Jupiter the way our moon dominates Earth. Jupiter is simply too massive. The Galilean moons create tides in Jupiter's atmosphere and interior, but the effects are proportionally smaller than the tides our moon creates on Earth. Saturn's moon system is equally impressive. Saturn has 146 known moons, including Titan, the second largest moon in the solar system, and the only moon with a thick atmosphere. Titan's atmosphere is denser than Earth's, composed mostly of nitrogen with some methane. It has weather patterns, clouds, rain, though the rain is methane, not water, and it falls into methane lakes on the surface. Titan is strange and wonderful, a world with active geology driven by cryovolcanism. Volcanoes that erupt with water ice instead of molten rock. It's a place where the familiar processes we see on Earth, weather, erosion, sedimentation, occur with exotic chemistry at extreme cold. Enceladus, another of Saturn's moons, is much smaller than Titan, but possibly even more interesting. It has active geysers erupting from its south polar region, shooting water ice into space. Some of this ice falls back to the surface, but some of it escapes to form one of Saturn's rings. Enceladus, like Europa, appears to have a subsurface ocean, and those geysers are giving us direct access to material from that ocean. Scientists have analysed the composition of the geyser plumes and found organic molecules, chemical building blocks that on Earth are associated with life. This doesn't mean Enceladus has life, but it does mean it has the right ingredients. It's another place where life might exist independent of the Sun, surviving on chemical energy in a dark ocean beneath an icy crust. Uranus and Neptune have moon systems too, though they're less well studied than Jupiter's and Saturn's. Miranda, a moon of Uranus, has some of the most bizarre terrain in the solar system, enormous canyons and terraced features that suggest a violent geological past, possibly including the moon being shattered and reassembling itself. The physics of that is still debated, but it's a reminder that moons can experience catastrophic events and survive. Triton, Neptune's largest moon, is another oddity. It orbits Neptune backward, retrograde, which strongly suggests it's a captured object, probably a Kuiper belt object that was grabbed by Neptune's gravity. Triton has active geysers too, erupting nitrogen gas that's been warmed by the faint sunlight reaching Neptune's orbit. Looking at all these moons, at their diversity and strangeness, helps us appreciate what we have. Our moon isn't the largest, that's Ganymede. It's not the most geologically active, that's Io. It doesn't have an atmosphere like Titan or geysers like Enceladus. It's actually quite simple, geologically speaking, just a ball of rock, cratered and ancient, with no atmosphere, no water, no volcanic activity. But what our moon does have is the perfect relationship with Earth. It's large enough to matter, to significantly affect our planet's rotation and climate stability. It's close enough to create strong tides and appear large in our sky. It's far enough to be stable in its orbit for billions of years, and it's been there for essentially all of Earth's history, giving life time to evolve in the stable conditions it provides. No other planet has this. Mars's moons are too small, and, in Phobos's case, temporary. The giant planet's moons are impressive, but they orbit planets so massive that the moons are proportionally insignificant Venus, and Mercury have no moons at all. Earth won the moon lottery. We have exactly the right moon for supporting a stable, habitable planet over geological time. And we've been exploring what happens if we lose that perfect companion, if that ideal relationship is broken. Saturn's rings, which we've used as a comparison for what Earth's rings might look like, are thought to be relatively young in cosmic terms. They might be the remnants of a moon that was destroyed, either by collision or by tidal disruption when it wandered too close to Saturn. They're beautiful, iconic, one of the most recognizable features in the solar system. But they're also a kind of monument to destruction, a reminder that moons can be lost. And here's an uncomfortable thought. It's happened before, elsewhere in the solar system. Moons have been destroyed. Mars will lose Phobos eventually. Saturn's rings might be the remains of a shattered moon. The universe doesn't guarantee that moons stay intact forever. We've been fortunate. Our moon has been stable for over 4 billion years. It's been there, constant and reliable, doing its job of stabilizing Earth and creating tides and lighting our nights. We take it for granted because it's always been there, because it seems permanent. But moons can be lost. And while our moon is very unlikely to explode, there's no physical mechanism that would cause it to. The thought experiment we've been exploring helps us understand what we'd lose if it did not just a light in the sky, but a fundamental component of what makes Earth habitable. Looking at other moons in the solar system, we see that each moon is unique. Each has its own story. Each affects its planet differently. But none of them have the relationship with their planet that our moon has with Earth. None of them are as important to their planet's habitability. Europa's subsurface ocean might harbour life, independent of its moon status. It's the tidal heating from Jupiter that matters, not Europa's own properties. Titan's thick atmosphere makes it fascinating, but it doesn't do for Saturn what our moon does for Earth. The moons of the outer solar system are wonderful, strange, worth studying and exploring, but they're not comparable to our moon in terms of their importance to their planet's habitability. Our moon is special, not the largest, not the most geologically active, not the most exotic, but special in the way it relates to Earth, in the stability it provides, in the perfect balance of size and distance that creates strong tides without disrupting orbits, that stabilizes rotation without locking it, that lights our nights without being too bright. Losing it would make Earth more like other planets in the solar system, less stable, less predictable, less uniquely suited for complex life. We'd become more ordinary in a cosmic sense, less of a special case and more of an average planet orbiting an average star. And while there's nothing wrong with being average, there's something precious about being special, about having the right moon in the right orbit, creating the right conditions for life to flourish. That's the gift we've been given, the gift we've been imagining losing. The solar system is full of moons, but Earth's moon is the one that matters most. Not because it's the biggest or the most interesting to planetary scientists, but because it's ours, and because it's exactly what we need. We've explored the physics and the ecology and the long-term consequences. Now, let's talk about something less quantifiable, but no less real. What the moon means to us. Not as a gravitational influence or a tidal force, but as a presence in human consciousness, in our art and stories and sense of ourselves. The moon has been part of human culture for as long as there has been human culture. Every civilization that's ever existed has looked up at the moon and seen something significant. They've told stories about it, built calendars around it, used it to navigate and mark time and understand the cosmos. Ancient peoples didn't know about tides or axial stability. They couldn't calculate the moon's mass or orbital period, but they knew the moon mattered. They could see it change shape through its phases, could watch it rise and set, could use it to track the passage of time. The moon was their clock, their calendar, their companion in the night sky. Different cultures saw different things in the moon's surface markings. In Western cultures, we see the man in the moon, a face formed by the darker Maria and lighter highlands. Chinese and Japanese cultures traditionally see a rabbit pounding rice or making mochi. Some Native American traditions see a woman's face. Aztecs saw a rabbit. Pacific Islanders saw different animals and figures. None of these are objectively there, of course. They're pareidolia, our tendency to see patterns and faces in random shapes. But the fact that every culture saw something, that everyone looked at the moon and found meaning in its markings, tells us something about our relationship with it. The moon has always been a canvas for human imagination. Lunar deities appear in almost every mythology. Selene in Greek mythology, Lunar in Roman, Khonsu in Egyptian, Tsukuyomi in Japanese Shinto, Chandra in Hindu tradition, Mamaquilla in Inca mythology. Sometimes masculine, sometimes feminine, sometimes associated with time, sometimes with madness. The word lunatic comes from lunar after all, but always important, always significant enough to warrant a god. The moon's phases made it natural for tracking time. A lunar month, the time from new moon to new moon, is about 29.5 days. This is long enough to be useful, but short enough to observe multiple times per year. Many cultures developed lunar calendars, tracking months by the moon's cycle. The Islamic calendar is purely lunar, with 12 months of either 29 or 30 days. This means Islamic months drift relative to the solar year. Ramadan, for instance, occurs at different times in different years relative to the seasons, but it creates a calendar that's simple and directly observable. You don't need astronomical calculations to know when a new month starts. You just look at the sky. The Jewish calendar is lunar-solar, combining lunar months with a solar year by occasionally adding an extra month. This keeps religious holidays aligned with seasons while maintaining the lunar month structure. The traditional Chinese calendar works similarly, which is why Chinese New Year falls on different dates each year in the Gregorian calendar, but always begins with a new moon. Even our word month comes from moon. The connection between lunar cycles and our measurement of time is so fundamental that it's embedded in our language. A month was originally one moon cycle. The fact that our modern months don't align with lunar phases anymore, that our calendar is solar rather than lunar, is a relatively recent development in human history. The moon has been a navigation tool for thousands of years. Sailors used it to determine latitude and to see by on dark nights. The moon's position relative to stars changes predictably, and skilled navigators could use this to track their position. Pacific Islanders were particularly skilled at lunar navigation, using the moon along with stars, waves, and other natural cues to voyage thousands of miles across open ocean. And there's the romance of moonlight. The aesthetic quality of how moonlight transforms familiar landscapes, making them seem different, dreamlike, special. Countless poems describe moonlight on water, moonlight through trees, moonlight on a lover's face. It's a whole category of human aesthetic experience that would be lost without the moon. Beethoven's Moonlight Sonata wasn't originally called that. The name was added later, inspired by a poet's description of the first movement as resembling moonlight on Lake Lucerne. But the name stuck because people understood immediately what moonlight meant aesthetically. That gentle, ethereal quality, that sense of something familiar, made mysterious and beautiful. In literature, the moon appears constantly. It's a symbol of romance, of mystery, of madness, of time passing. Once in a blue moon means rarely, because the second full moon in a calendar month is uncommon. Many moons ago means long ago, time measured in lunar cycles. Over the moon means extremely happy, perhaps because the moon seems so high and unattainable. Werewolf legends connect transformation to the full moon. The idea that people might change under lunar influence is ancient and widespread. It's not based on reality. Studies have shown no correlation between moon phases and human behavior, despite persistent beliefs to the contrary. But it's a powerful cultural idea, the moon as something that affects us, that has power over human nature. The space age added new layers to our relationship with the moon. When Lunar 2 crashed into the moon in 1959, it was the first human-made object to reach another world. A profound milestone. We'd touched something beyond Earth. We'd proven we could leave our planet and reach out into the cosmos. And then, of course, there was July 20th, 1969. Apollo 11. Neil Armstrong stepping onto the lunar surface and speaking those famous words. That's one small step for man, one giant leap for mankind. 600 million people, about 1/5 of Earth's population, watched on television. It was one of the most watched events in human history. The moon landings represented something more than technical achievement. They were philosophical statements. They proved that humans could leave our planet, could survive in space, could explore other worlds. They suggested that our future might not be limited to Earth, that we could become a spacefaring civilization. The fact that we haven't returned to the moon since 1972 is sometimes seen as a failure of ambition, but those missions still matter. They proved it was possible. They brought back samples that have taught us about the moon's formation and history. They left equipment on the surface that's still being used, retroreflectors that scientists bounce lasers off to measure the moon's distance with incredible precision. And they left footprints. In the airless environment of the moon with no wind or rain to erode them, those footprints could last for millions of years. They're a monument to human achievement, a mark that says, we were here, preserved in lunar dust until some future impact or geological process erases them. Losing the moon would mean losing those historical sites, the Apollo landing sites, the various rovers and landers from different countries, the flags and footprints and plaques. When the moon exploded, all of that would be destroyed. Our first tentative steps into space would be erased, the sites of our greatest achievements scattered into debris. There's also the cultural loss of lunar timekeeping. So many traditions are tied to moon phases. The Chinese Mid-Autumn Festival, celebrated at the full moon of the 8th lunar month, the Jewish holiday of Passover, which begins on the full moon of the first month of spring, Islamic months beginning with the sighting of the new crescent moon. All of these would lose their astronomical anchor. Future generations would still celebrate these holidays. Presumably, cultural practices are persistent, but they'd be disconnected from the celestial event that originally defined them. You'd celebrate the Mid-Autumn Festival without being able to see the autumn moon it's named for. You'd look for a crescent moon that doesn't exist to mark the beginning of Ramadan. The poetry would persist too, but it would become historical. Future people reading The Moon and Sixpence, or Moonlight in Vermont, or How High the Moon, would need footnotes explaining what a moon was, what moonlight looked like, why these were romantic and poetic rather than technical terms. The shared cultural reference would be lost. And children growing up after the explosion would hear stories about the moon, the way we hear stories about dinosaurs, as something that used to exist, that's gone now, that they can only know through pictures and descriptions grandparents would tell them, "I remember when we had a moon," and they'd try to imagine it, but imagination isn't the same as experience. There would be new cultural developments too, presumably. Poets would write about the rings instead of the moon. New holidays might be based on ring phenomena, the shadow bands, the ring shine patterns. Navigators would develop new techniques using stars and rings instead of the moon. But it would take time for these new traditions to develop, to gain the depth and resonance that lunar traditions have. The moon has been part of human consciousness for tens of thousands of years. That's not replaced quickly. The cultural void left by the moon's absence would be felt for generations. Museums would preserve moon rocks, display videos of the moon's phases, maintain exhibits about what the moon was and what it meant. Children on field trips would look at these exhibits and learn about the moon the way they learn about ancient civilizations or extinct animals, as something that existed, that was important, that's gone now. And there would be people who remembered. For decades after the explosion, there would be people who grew up with the moon, who remember seeing it in the sky, who can describe what moonlight looked like and how the phases changed and what it felt like to watch a lunar eclipse. They'd be living connections to a world that no longer exists. Eventually those people would age and die, and the last person who actually saw the moon would pass away. It would be a milestone, like the last person who remembers a major historical event. The last living connection to the pre-explosion world would be gone, and the moon would be entirely historical, only knowable through records and artifacts and second-hand accounts. There's something profoundly sad about that transition, the move from something we have to something we remember, to something we know only from history. It's the loss not just of the moon itself, but of the living experience of the moon, of the direct connection between present people and that ancient companion. But culture would continue. Humans would adapt, would find new ways to mark time and navigate and create beauty. We'd develop new traditions, new poetry, new ways of relating to the night sky. The rings might become as culturally significant as the moon once was. Given enough time, people might not miss the moon because they'd never known a world with one. But we would know, we living now who've seen the moon our entire lives, who've grown up with it as a constant presence, we'd know what was lost. We'd remember what the night sky looked like with a moon instead of rings. We'd carry that memory, that knowledge of what we had and what we lost for the rest of our lives. The moon in human culture isn't just about tides and light. It's about meaning, about how we understand time and beauty and our place in the cosmos, about the stories we tell and the traditions we maintain, and the sense of continuity across generations. Losing the moon would mean losing more than a celestial object. It would mean losing a piece of human identity, a connection to every human who came before us, a shared reference point that's united our species across all of history. And that loss, unmeasurable as it is, might be the most profound consequence of all. And so we reach the end of our journey through this impossible scenario. We've imagined the moon shattering, watched debris fall from the sky, explored Earth with rings instead of a companion. We've walked through the loss of tides, the instability of climate, the darkness of nights without moonlight. It's been quite a journey, hasn't it? Through catastrophe and consequence, through immediate disaster and long-term change, through the physics of what would happen and the meaning of what we'd lose. But here's what we return to. The moon is still there. Right now, as you listen to this, the moon is orbiting Earth just as it has for 4.5 billion years. Stable, predictable, constant. It will rise tonight, or if it's daytime where you are, it's up there somewhere. Invisible against the blue sky, but present nonetheless. The moon isn't going anywhere. Moons don't explode. They don't shatter. They just quietly orbit their planets, doing what they've always done, being what they've always been. Our moon will be there tomorrow night, and the night after, and for billions of nights to come. We explored loss to understand value. We imagined destruction to appreciate stability. We contemplated darkness to cherish light. And now we can look up at the moon, tonight, next week, whenever you next see it in the sky, and perhaps appreciate it a little more. See it not just as a light in the darkness, but as the companion that stabilizes our planet, that creates our tides, that's been watching over Earth since before there was life here. If you've enjoyed this exploration of what we'd lose if the moon exploded, if these late-night wanderings through impossible scenarios resonate with you, I'd be grateful if you'd subscribe to the Sleepy Astronomer. There are more cosmic questions to explore, more ways to appreciate the universe we actually inhabit by imagining the universes we don't. And if this particular journey meant something to you, a gentle like helps others find their way to these quiet contemplations of space and time. Thank you for travelling with me tonight, for imagining the impossible, and for being curious about how the universe works and what makes our world special. The moon is still there. You're still here. And that ancient relationship between our planet and its companion continues, unchanged by our imagination, untroubled by our exploration of catastrophe. The tides will rise and fall tomorrow, just as they did yesterday. The moon will light the night, just as it always has. That continuity, that stability, that reliability, it's a gift. Not from the universe, which doesn't give gifts, but a gift nonetheless. A fortunate arrangement of mass and gravity and orbital mechanics that happens to create exactly the conditions we need. Sleep well, watched over by our constant companion. Dream of rings and meteor showers if you like. They make for interesting dreams. But wake to the reality we're blessed with. A stable planet with a stable moon, orbiting a stable star in a quiet corner of a vast and ancient galaxy. Good night from the Sleepy Astronomer. May your dreams be peaceful, and may the moon be there when you look for it, just as it's been there every night of every life that's ever been lived on Earth. Until we meet again, under the light of our ancient companion,